Jupiter isn't a peaceful planet, it's a planet-sized weapon, spinning storms bigger than Earth, forging radiation that can kill electronics in minutes. Up close, that bright planet in our night sky becomes a magnetic trap so vast it could swallow worlds. So why did this monster both threaten the early solar system and somehow protect Earth long enough for us to exist? In Jupiter's realm, space itself becomes hostile. Light turns to static and silence can arrive without warning. The planet does not need a surface to be lethal, it only needs time. For most of human history, Jupiter was a god's lantern, steady, bright, and seemingly untroubled by the chaos around it. But the closer our instruments listen, the more that serenity unravels. Because this world is not defined by land or sea, it is defined by forces. Jupiter is a place where the familiar rules of weather and orbit are rewritten at overwhelming scale, where motion becomes a machine, and the machine never sleeps. Its power is not theatrical, it is structural, embedded in rotation, pressure, and fields we cannot see. And that is what makes it frightening in a way volcanoes and impacts are not. Jupiter's danger does not need to strike once, it can persist. Tonight's story follows a simple idea with unsettling consequences. The most beautiful object in the night sky can be the solar system's most efficient engine of disruption. Jupiter can sculpt paths through space with patient precision, rearranging trajectories until chance becomes destiny. It can turn the region around it into a map of invisible boundaries, thresholds you cross only once, because hardware, shielding, and human biology all have limits. Yet the same planet that threatens can also steady the system it dominates, an indifferent architect whose influence reaches far beyond its clouds. To understand how, we have to stop thinking of Jupiter as a planet in the comforting terrestrial sense. We have to treat it as a dynamic environment, one that generates its own hazards, feeds them, and extends them outward through a vast domain of charged particles and gravity. Across this journey, we will follow the evidence left by telescopes, by battered spacecraft, and by the mathematics of motion. We will watch tranquil bands become signatures of deep heat and relentless circulation, then descend conceptually into an interior where matter changes its nature under crushing pressure. And we will widen our view until Jupiter's true footprint appears, written into gaps, resonances, and impacts across the solar system. The question is not whether Jupiter is powerful. We have always known that. The question is what that power has done, over billions of years, to everything else that tried to share the sun with it, and why our own world is still here to ask. This is not a tale of a peaceful giant. It is a guided encounter with planetary power at its most absolute, beautiful at a distance, merciless up close, and impossible to ignore once you understand what it really is. Before we begin, let us know in the comments below where in the world you're watching from and what time it is there. Now, settle in for a journey. We begin with the calm illusion in our night sky, then move outward into an empire you cannot see and a hazard you cannot outrun. From storms to deep physics to gravity's long game, each chapter pulls us closer to Jupiter's true role in our history. Jupiter rises the way it always has for most of human history, a bright point that keeps its place with patient certainty. It looks like a steady pale jewel pinned near the ecliptic, bright enough to command attention without shouting. It does not twinkle much because its apparent disk is large enough to average out atmospheric turbulence. To the naked eye, that steadiness reads as calm, and calm reads as safe. Ancient skywatchers noticed that calm and gave it meaning, folding the planet into myth and omen. The wandering star moved against the fixed constellations, yet it moved with a dignity that felt almost deliberate. Even its name carries that weight, Jupiter, King of Gods, because brightness invites authority. From a backyard it feels distant, orderly, and almost friendly. That first impression is the lie this documentary is built to break. Jupiter is beautiful in the way a blade can be polished, reflecting light while keeping its edge. The danger is not obvious from Earth because the worst parts are invisible, and invisibility is a powerful disguise. The violence is not a single event with a beginning and an end. It is a system that never stops running, even when no one is watching. From our backyard scale, Jupiter is a dot that moves slowly night to night, sliding along the zodiac like a bead on a wire. Through a small telescope, it becomes a disk with stripes and moons, and the mind relaxes into recognition. Those moons line up like a miniature solar system, a neat demonstration of gravity's order. Even then, the scene can feel serene, like weather on a faraway globe that cannot reach you. But the serenity is a trick of distance and scale, and distance is a kind of mercy. When early telescopes first resolved Jupiter's bands, they looked like decorative brushstrokes across a polished sphere. When Galileo tracked the 4 bright moons, he saw clockwork, not chaos. The human brain prefers patterns it can hold, and Jupiter offers patterns first. Spacecraft did not agree with that story. When probes and orbiters measured Jupiter up close, the numbers refused to stay abstract because instruments do not negotiate with awe. The planet's size alone changes what words like weather and distance mean, and it changes them immediately. Jupiter is about 11 Earths across in diameter, which means you could line up Earth end to end and still not span the disk. If Earth is a room, Jupiter is the building, and the building has no solid floor. The scale is not only wide, it is deep, because Jupiter is mostly fluid down to pressures we can barely simulate. The clouds we see are not the surface, and calling them a surface is already a mistake. Beneath them, hydrogen becomes dense, then stranger, then metallic under crushing pressure. That layered interior matters because it powers the field and feeds the heat that drives everything above. Mass is the next step in the shock, and it is the step that turns beauty into leverage. Jupiter is 318 Earth masses, a third of 1,000 Earths packed into one object, and gravity follows mass without apology. It is not just large, it is dominant, second only to the Sun in the solar system's hierarchy. Dominant means that other bodies do not merely coexist with Jupiter, they negotiate with it constantly, whether they know it or not. Dominant means gravity that writes the rules for others, not in metaphor but in mathematics. Jupiter's pull shapes the paths of asteroids, comets, and even planets by altering their orbital energy and timing. It captures, ejects, and redirects bodies that would otherwise wander, sometimes with a gentle nudge that becomes catastrophic over millennia. It is a gatekeeper that can open the gate by accident, because small changes accumulate into large outcomes. Dominant also means angular momentum that the solar system has to share, like a budget that cannot be ignored. Jupiter holds most of the planetary angular momentum, so its motion is not a detail at the edge of a diagram. It is a major part of the system's balance sheet, and that balance sheet constrains what the rest can do. When Jupiter shifts, everything else feels it, even if the shift is slow and silent. This is where the calm dot becomes a threat, because threats do not need proximity to be real. A massive object does not need to touch you to harm you, and it does not need intention. It can change your orbit, your impact rate, your long-term stability, and it can do it while remaining visually unchanged. The danger begins with gravity, long before any atmosphere, long before any cloud. Yet gravity is only the first layer, and Jupiter is terrifying because it is energetic in multiple ways at once. It radiates more heat than it receives from the Sun, which means it is not merely reflecting sunlight like a cold marble. It is still cooling and contracting, still releasing stored formation energy through slow compression. In plain terms, Jupiter is warm from the inside, and that warmth has consequences. That internal power feeds an atmosphere with no solid surface to slow it, no continents to break winds, and no oceans to buffer storms. Jupiter's clouds are not a thin skin over rock. They are the visible top of a deep convecting engine, where rising heat drives circulation on a planetary scale. The planet is a machine made of fluid, rotation, and heat, and machines do not get tired. From Earth, the bands look like gentle brushstrokes laid across a globe. Up close, they are jet streams that wrap the planet at extreme speeds, stacked in alternating directions like belts on a spinning turbine. The banded appearance comes from differences in temperature, chemistry, and vertical motion, which change how clouds form and how they reflect light. Storms are not local accidents that blow through and vanish. They are structural features that can outlive human lifetimes, because the energy supply is continuous. The Great Red Spot is the famous example, but it is not the only one, and fame can hide the larger pattern. Jupiter's atmosphere hosts cyclones at the poles, arranged in geometric clusters that look almost designed when seen from above. It hosts turbulence at every latitude, where shear between jets tears clouds into filaments and curls. Lightning flashes inside clouds of ammonia and water, and those flashes reveal deep convection like a heartbeat under the visible deck. The planet's weather is not weather like ours, because the boundary conditions are different. On Earth, weather is shaped by land, oceans and a thin atmosphere over a solid surface. On Jupiter, weather is shaped by depth, rotation, and heat rising from below, with cloud layers marking chemistry rather than ground. The colours are not paint, they are molecules, ammonia ice, ammonium hydrosulfide, and complex photochemical hazes altered by sunlight. When the winds shear those layers, the planet becomes a moving map of physics. Still, the storms are only one of the three main threats we will follow, and they are the most visible, which makes them deceptively familiar. The second threat is radiation that can kill electronics and biology, even when the sky looks clear. The third threat is magnetism on a scale that makes the word environment feel inadequate, because it creates a region of space that behaves like part of the planet. Together they turn Jupiter into a kind of weapon, not by malice but by sheer capability. To understand why, we have to stop thinking like stargazers and start thinking like engineers approaching a hazard zone. A spacecraft does not care that Jupiter is pretty, and it does not care that we want it to be a destination. It cares about particle flux, field strength, charging, and the time it can survive before systems degrade. In that language, Jupiter is not a postcard. It is a test chamber. Jupiter's radiation belts are the first warning sign, and they are not a minor complication. They are filled with charged particles accelerated to lethal energies, including electrons moving near the speed of light. They are trapped and whipped around by the planet's magnetic field, gaining energy as they spiral and bounce between hemispheres. In places, the dose is so intense that unshielded systems fail quickly, and even shielded systems age in days what they might otherwise age in years. Those belts are not a thin ring you can simply avoid by choosing a clean trajectory. They are a layered region with gradients, spikes, and changing conditions that depend on solar wind pressure and internal sources. They are fed by the Sun, but they are also fed by Jupiter's own moons, which supply material that becomes plasma. The belts are shaped by a magnetosphere that breathes under solar wind pressure, expanding and compressing like a lung made of magnetic field lines. This is why calling Jupiter peaceful is dangerous, because peaceful implies stable, gentle, and safe to approach. Jupiter is stable in the way a loaded spring is stable, holding energy in a configuration that can do work. It holds energy and releases it through predictable physics, and predictable physics is still physics. Predictable does not mean survivable, especially when the numbers are so large. Now the third threat, the one that makes Jupiter feel unreal even to people who study it for a living. Jupiter's magnetic field is the strongest of any planet in the solar system, generated by a dynamo deep inside where metallic hydrogen conducts electricity. That field creates a magnetosphere so vast it becomes a world of its own, with boundaries, currents, and weather-like variability. It is not a bubble around the planet in the casual sense, it is a domain. On the day side, the solar wind compresses that domain, pushing the magnetic boundary inward like a hand pressing on a drumhead. On the night side, it stretches into a long magnetic tail, drawn out by the flow of charged particles from the Sun. Under certain conditions, that tail can extend towards Saturn's orbit, a reach so large it reframes what near Jupiter means. The exact reach changes with solar activity, but the scale stays monstrous. Inside that magnetosphere, particles spiral along field lines and slam into moons, and those impacts matter. Auroras blaze near the poles, powered not just by sunlight, but by magnetospheric currents that dump energy into the upper atmosphere. The system is wired like a generator because the planet spins and the field drags plasma with it, forcing charged particles to corrotate. When that corrotation slips, energy is released, and the release is visible as light at the poles. Jupiter's rotation is another hidden amplifier, and it is fast enough to feel almost wrong for something so large. A day on Jupiter is about 10 hours, so the planet spins rapidly for its size, and that rapid rotation strengthens the dynamo in its interior. It also drives the atmospheric jets by organizing turbulence into bands, a known effect of rotating fluids. Rotation helps energize the magnetosphere as well, because it couples the planet's interior to the space around it. So the three threats are linked, not separate hazards stacked by coincidence. Fast rotation helps build a strong magnetic field, and the strong field traps particles into radiation belts. The internal heat and rotation drive storms that can span continents, then entire hemispheres, while the magnetosphere reaches outward and makes space itself part of the system. Jupiter is not three dangers in one place. It is one engine expressing itself in three different ways. This chapter is not here to list hazards like a manual. because a manual implies you can simply follow steps and be safe. It is here to set the stakes for a bigger question that runs under everything we will see. Jupiter is not only dangerous up close, where its belts and fields can shred hardware. It has been shaping the solar system since before Earth existed, and that shaping is part of the threat. Giant planets are architects of planetary systems, and we see their influence in exoplanet surveys as well as in our own backyard. Their gravity sculpts disks of gas and dust, shepherds material into resonant patterns, and clears regions by scattering smaller bodies. They can migrate inward or outward during formation, trading angular momentum with the disk in a slow gravitational conversation. That migration can rearrange everything that tries to become a planet, and it can decide which worlds are allowed to exist. Jupiter's early history likely changed where rocky worlds could form and how much material remained in the inner system. It influenced the distribution of water and volatiles, the ingredients that make atmospheres and oceans possible. It helped decide which bodies stayed in stable orbits and which were scattered into collisions or exile. The solar system we live in is partly Jupiter's design, even if the design was not intentional. But an architect can also be a disruptor, because the same tools that build can also break. Jupiter can increase impact rates by perturbing small bodies into Earth-crossing paths, nudging them through resonances that destabilize their orbits. It can also reduce impacts by ejecting comets from the system, flinging them outward so they never return. The same gravity that protects can also aim, and the difference can depend on timing. That dual role is the heart of the central question, and it resists simple labels like guardian or villain. What makes Jupiter genuinely terrifying is not only its local violence, where radiation and storms dominate. It is the way its power reaches across space and time, influencing probabilities rather than certainties. It can shape the odds of catastrophe on worlds that never come near it, and odds are how extinction often arrives. When we say Jupiter dominates, we mean it sets the tempo for many solar system processes, like a metronome that others cannot ignore. Resonances in the asteroid belt are tied to Jupiter's orbit, carving gaps where orbits become unstable over long periods. Trojan asteroids share its path like captured debris, clustered near gravitational balance points that are stable in a mathematical sense. Comets from the outer regions feel its influence as they fall inward, and many of them leave on new trajectories. Even Earth's long-term safety is connected to this giant, and that connection is written into stone. The impact history written into craters and extinctions is partly a story of orbital dynamics, not only of random chance. Jupiter is one of the main authors of that story because it controls pathways through which small bodies move. It writes in gravity, not ink, and the writing can take millions of years to read. This is why the calm dot in the sky matters, even if it never seems to change. It is not just another planet to admire during a clear evening. It is a massive engine that never shuts off, humming through the solar system's architecture. It is a storm world, a radiation furnace, and a magnetic trap that can swallow the space around it. The beauty is real, but it is not the point, and that is the uncomfortable lesson. Beauty can distract you from scale and energy, because beauty invites closeness and trust. Beauty can make you forget that nature does not offer peace as a default, and it never signs a safety contract. Jupiter is not angry, and it is not cruel. It is simply powerful, and power is indifferent. As we move forward, we will treat Jupiter like a scene where the evidence is still moving, and where the suspect is the environment itself. The clouds shift, the fields flex, the particles surge, and the moons feed the system with material and momentum. Nothing is frozen for inspection, and nothing waits for us to be ready. The crime scene is alive. We will follow the three threats in detail, because each one reveals a different face of the same machine. We will see how radiation belts form and why they are so intense, and we will measure what lethal means in numbers. We will track storms and the deep atmosphere that powers them, where convection and chemistry paint the clouds from below. We will map the magnetosphere and the currents that make it enormous, and we will watch it respond to the sun. We will also keep the cosmology angle in view, because Jupiter's present danger is tied to its past role in building the solar system. Its moons, its composition, and its orbit are clues to migration and formation, clues preserved in motion and chemistry. Understanding Jupiter is partly understanding why Earth exists at all, and why Earth has had the history it has. If Jupiter had been slightly different, Would the inner planets have survived the early chaos? The closer you get, the less Jupiter behaves like a planet, and the more it behaves like a regime, with rules enforced by fields and flux. It has borders made of magnetism, not walls, and those borders move as the solar wind changes. It has weather that is also physics, because fluid dynamics and rotation are inseparable there. It has hazards that begin far outside the clouds, where space is already charged and already moving. So we start where the lie is strongest, with the calm light in the night sky, steady and almost comforting. Then we push past the comfort of distance and the softness of the word beautiful, because beauty is not a shield. The real story begins before you reach the atmosphere, before you see the bands fill the frame. It begins in the invisible space that surrounds the planet like an unseen ocean. Now we dive from the cloud tops into the invisible space around Jupiter. The first danger is not a storm you can see, not a red vortex or a bright lightning flash. It is the environment that waits in the dark, already charged, already moving, already lethal. Now we dive from the cloud tops into the invisible space around Jupiter. The first boundary of fear is not a surface or a storm, and it is not even something you can photograph directly. It is a magnetic domain that turns empty space into an active, changing machine. From a distance, the planet looks like a painted marble, smooth and self-contained in the black. Up close, the space around it behaves like a working engine, quiet in appearance, ruthless in effect. A magnetic field is a force field made by moving electric charges. In physics terms, it is the B field, one half of electromagnetism's paired structure with the electric field. It pushes and guides charged particles like electrons and ions through invisible lines of influence. Those lines are not literal wires, but they are useful maps for motion and stress. They show the direction a magnetic compass needle would point, and they hint at how plasma will move. A compass works because Earth's field gives direction to magnetic materials and moving charges. The needle aligns with the local field direction, and that alignment is a visible trace of an invisible geometry. On a planet with no global field, a compass becomes a dead object, no matter how carefully it is built. Around Jupiter, the same basic rule applies, but the scale changes everything. The field is not just a navigational curiosity, because it can dominate how matter behaves. To understand why, we have to name what space usually contains. Interplanetary space is never truly empty, even when it looks black and still from a human viewpoint. It holds thin gas, dust, and a constant drizzle of charged particles that can carry energy across huge distances. It also holds magnetic fields carried outward from the Sun, stretched into a spiral by solar rotation. Jupiter sits inside that flowing environment like a boulder in a river, and the river never stops. A magnetosphere forms when a planet's magnetic field meets the solar wind. The solar wind is a stream of charged particles flowing outward from the Sun, born in the hot corona and released into space. It is mostly electrons and protons, with traces of heavier ions moving at hundreds of kilometers per second. It carries energy, momentum, and its own embedded magnetic field, called the interplanetary magnetic field. When that stream hits a planetary field, it is deflected and forced around it. That interaction creates boundaries, like weather fronts in space, and those boundaries can be crossed in minutes. The solar wind cannot simply pass through a strong magnetosphere, because charged particles feel magnetic forces and respond collectively. Instead, the flow is slowed, heated, and redirected as it encounters resistance. The transition is not gentle, and it is not static, even when Jupiter looks calm. The border shifts as solar conditions change, and it can breathe in and out like a lung. The solar wind slows and piles up at a bow shock. This is a shock wave in plasma, similar in concept to the shock in front of a supersonic aircraft, but built from fields and particles. Upstream, the particles are fast and relatively ordered, streaming along with a shared direction. At the shock, their motion becomes more chaotic, and their temperature rises as energy is redistributed. Magnetic fields fluctuate, turbulence grows, and waves ripple outward in a restless, invisible surf. Farther in, pressure balances at the magnetopause, where solar wind and planetary field negotiate a moving border. The magnetopause is not a wall, but it behaves like one, because it separates two different regimes of control. On one side, the solar wind dominates and drags its own field lines along, bending them around the obstacle. On the other side, the planet's magnetic pressure and plasma populations take control. The exact location is a living compromise shaped by solar wind density, speed, and magnetic orientation. On Earth, that border is mostly protective, even though it can still be stressed and punctured. It reduces the solar wind's direct access to our upper atmosphere, and it helps limit radiation at the surface. When Earth's magnetosphere is disturbed, we see auroras and satellite anomalies, and sometimes power grids feel the consequences. Yet the system's overall role is still that of a shield, a buffer between a star and a fragile biosphere. Jupiter's magnetosphere is not simply a bigger version of Earth's. It is a different kind of environment, powered from within as much as from the Sun, and that distinction changes the story. Scale and rotation turn it from shield to accelerator, because stored energy is constantly replenished. The same physical laws apply, but the balance of forces is rearranged. In that rearrangement, protection becomes power, and power becomes a persistent hazard. Jupiter's magnetic field is generated by an internal dynamo. A dynamo is a natural electrical generator, created when conducting fluid moves through an existing magnetic field, even a tiny seed field. The motion induces electrical currents, and those currents reinforce the field in a self-sustaining loop. It is a feedback process that can persist for billions of years, as long as the interior keeps moving and conducting. Earth does this with molten iron in its outer core, and Jupiter does it with something stranger. Deep inside Jupiter, hydrogen is squeezed until it becomes liquid metallic hydrogen. Under immense pressure, hydrogen's electrons become less bound to individual atoms, and the fluid begins to conduct electricity like a metal. This is not a laboratory curiosity, although experiments try to mimic it in brief flashes. It is the material that makes Jupiter's dynamo possible, and it occupies a vast volume beneath the visible atmosphere. Metallic hydrogen conducts electricity, so moving flows there can build a planet-sized electromagnetic generator. Convection transports heat outward, and rotation organizes those flows into patterns that can sustain a global field over time. The dynamo is hidden under thousands of kilometers of atmosphere and fluid layers, far below any cloud we can see. Yet its effects reach far beyond the clouds, into space itself, where spacecraft can measure the field directly. Jupiter also spins fast for its size, and that speed is not a detail, it is a driver. A Jovian day is about 10 hours, so the interior rotates like a massive flywheel with enormous angular momentum. Rapid rotation strengthens the dynamo and organizes currents that keep the field intense and coherent. It also shapes the magnetosphere's behavior, because the field lines are anchored to a rapidly turning planet. The result is a magnetic system that insists on motion, even when the solar wind is quiet. When we talk about the field, we should separate two ideas that are often blended. Field strength describes how hard the field pushes on charged particles near the planet, setting the tightness of their spirals. Magnetosphere size depends on field strength and on solar wind pressure that can compress or relax the boundary. A strong field tends to make a large magnetosphere, but the solar wind can still squeeze it like a hand squeezing a balloon. Jupiter's system is large because it is strong, and strong because it is energetic. Jupiter's field is far stronger than Earth's at comparable locations. Near the cloud tops, it is measured in Gauss rather than fractions of a Gauss, and that difference matters immediately. In simple terms, a Gauss-level field can grip charged particles tightly, forcing rapid gyromotions around field lines. It forces them into tighter spirals and faster rotations, which reduces their ability to wander across the field. That grip is the beginning of confinement, and confinement is the beginning of danger. That strength matters because it controls how tightly particles are trapped and how violently they can be accelerated. In a weaker field, particles can wander more easily, and confinement is less efficient, so populations leak away. In a stronger field, their motion becomes organized, and organization is what makes storage possible. Storage turns a passing particle into a resident, and a resident particle can be energized again and again. The magnetosphere becomes less like a passing breeze and more like a reservoir with walls. The magnetosphere's size is where the numbers become unsettling. On the day side, the solar wind can push the magnetopause inward, sometimes to tens of Jupiter radii, depending on solar wind pressure. A Jupiter radius is about 71,000 kilometers, so tens is already millions of kilometers of controlled space. That is the distance between worlds, not the distance between clouds or continents. a spacecraft can be deep inside Jupiter's domain while still far from the planet's visible disk. On the night side, the same flow stretches the field into a long magnetotail. The tail forms because the solar wind drags magnetic field lines downstream, pulling them into a tapered structure like a banner in a gale. It is shaped by pressure differences, by reconnection events, and by the constant push of the solar wind against a rotating field. The tail is where energy can be stored like tension in a stretched rope. When it releases, the system can lurch and brighten. That tail is not a metaphor, even if our eyes cannot see it. It is a structured region of magnetic field lines and plasma, pulled away from the planet like a windsock, with layers and boundaries inside it. In visual terms, imagine a luminous comet tail, except it is made of invisible field geometry and thin plasma. It is threaded with currents and layered regions, each with different particle populations and temperatures. It can be calm for a time, and then suddenly reorganize, as if a hidden hand snapped the rope. Under certain solar wind conditions, the tail can extend enormous distances, sometimes described as reaching towards Saturn's orbit. That phrase is not a fixed measurement, and it is not always true, because the tail's length changes with solar wind speed and pressure. It's a statement about potential reach when the solar wind stretches the system into an extreme configuration. The key point is that Jupiter's influence can fill a huge fraction of the inner-outer solar system, and it can do so without any visible sign. When you picture this, do not picture a neat bubble with clean edges. Picture a living shape that breathes with the sun's mood, swelling and compressing as conditions change. The day side compresses under stronger solar wind pressure, and the night side elongates like pulled taffy behind a moving object. The boundaries ripple, and the internal plasma responds with waves, currents, and shifting populations. Jupiter's magnetic empire is not drawn in ink. It is drawn in forces. Inside the magnetosphere, space behaves less like vacuum and more like circuitry. Electric currents flow along field lines and across them, closing through plasma in loops that can span planetary distances. Plasma moves, heats, cools, and reorganizes as conditions change, responding to both external pressure and internal rotation. In a circuit, current follows conductors and returns along defined paths. In a magnetosphere, the wires are magnetic field lines and plasma channels, and the components are regions of different density and temperature. The solar wind sculpts the whole structure in real time. Increased solar wind pressure compresses the day side, raising particle densities and shifting boundaries inward, sometimes abruptly. Decreased pressure lets the magnetosphere expand, changing where trapped particles can circulate and where waves can grow. The result is a system with moving walls and shifting internal traffic, where yesterday's quiet region can become today's corridor of turbulence. A safe corridor can become a hazard zone without warning. This is the first reason near Jupiter is misleading. You can be far from the clouds and still be inside Jupiter's domain, already immersed in its field and plasma. The planet's true border is not its atmosphere, but the moving magnetic frontier far beyond it. For navigation and engineering, that frontier matters more than the visible limb, because it marks where the environment begins to change. It is the moment when space stops behaving like deep space. The second reason is that Jupiter's magnetosphere is powered by rotation. Earth's magnetosphere is largely driven by the solar wind's energy input, which makes it responsive and episodic. Jupiter's is driven by the planet's spin-forcing plasma to corrotate, and that makes it continuous and insistent. That difference is subtle in words, but enormous in consequences because one system is primarily reactive while the other is continuously driven. It is the difference between a shield that braces and a machine that runs. Corrotation means the magnetosphere tries to spin with the planet. Jupiter's field lines sweep around, dragging charged particles with them, and the motion is fast enough to be felt as a persistent electric influence. If the plasma were perfectly locked to the field, it would rotate at nearly the same angular speed as the planet, like beads frozen into a turning wheel. But plasma has inertia, and it is constantly being added and redistributed by sources within the system. The system struggles to enforce that rotation, and the struggle generates power. When plasma cannot keep up, the system generates electric fields and currents that pump energy back into the plasma. These are not small corrections, because they involve planet-scale potential differences and vast current systems. They are large-scale electrodynamic responses that couple different regions together, linking the equator to the poles. Currents can flow along field lines into the polar atmosphere and back out again, completing loops through space. The magnetosphere becomes a linked machine, with Jupiter's rotation as the motor. This turns the magnetosphere into a giant generator and motor at once. Rotational energy is converted into particle energy, and that conversion can be steady rather than rare. The result is a space environment that can act like an accelerator, not a passive bubble that merely deflects the wind. In an accelerator, particles are guided, confined, and energized repeatedly until they become dangerous. Jupiter does the same thing, using magnetic geometry instead of steel vacuum pipes. The moons feed this machine, and the system rewards that fuel with violence. Material from moons becomes ionized and joins the plasma population, increasing density and providing fresh particles to energize. Once charged, it is captured by the field and forced into Jupiter's rotating electromagnetic regime, where it can be heated and transported. Neutral atoms become ions when sunlight, collisions, or energetic particles knock electrons free. The moment that happens, the particle's fate changes, because it begins to feel the field's grip. This idea has a history, because it was not obvious at first and it was not easy to measure. Early spacecraft hinted that Jupiter's environment was extreme, but the reasons took time to untangle, and arguments took years to settle. Pioneer and Voyager measured fields and particles that exceeded expectations, and they returned data that forced new models. Later missions refined the picture, showing that internal sources and rotation mattered profoundly, not just the Sun. The magnetosphere was not merely a solar wind bubble. It was a planetary system with its own metabolism. Even before we focus on radiation belts, we need the concept of trapped motion. Charged particles do not move straight through a magnetic field, because the field bends their paths without touching them. They spiral around field lines, bounce between hemispheres, and drift around the planet in looping paths that can persist for days or longer. This is basic plasma physics, and it is the foundation of the hazard. The particle's path becomes a choreography imposed by the field, and the choreography repeats. The spiral motion happens because a moving charge feels a force perpendicular to its velocity and the magnetic field. That force bends the path into a circle, and the combination of forward motion and circular motion becomes a helix around the field line. The tighter the field, the tighter the helix, and the more firmly the particle is tied to the geometry. The faster the particle, the larger the circle, but the confinement remains unless collisions or waves scatter it. Around Jupiter, confinement is efficient, and efficiency means accumulation. The bouncing happens because the field is stronger near the poles. As particles move into stronger field regions, their spiral tightens, and their forward motion can be reflected, as if the field becomes a magnetic hill. This is called magnetic mirroring, and it creates a back-and-forth motion between hemispheres along a single field line. The particle becomes a traveller on a magnetic rail shuttling between two turning points above the atmosphere. Each pass is another opportunity for interaction, and interactions can change energy. The drift happens because the field is not perfectly uniform. Gradients and curvature cause particles to drift sideways, slowly circling the planet, and that drift depends on charge and energy. Electrons and ions drift in opposite directions, which can create currents that are not mere side effects. Those currents can modify the field and generate waves, and the waves can feed back into particle motion. The magnetosphere becomes a self-modifying system, shaped by the very particles it traps. Those motions create storage. Particles can remain trapped for long times, gaining energy through waves and electric fields, and losing it only slowly. Trapped populations become belts, and belts become hazards that do not require a solid surface to be deadly. The danger is statistical and cumulative, like standing in a rainstorm of bullets, where probability becomes destiny. You do not need to be hit by many to fail, and you cannot see them coming. Jupiter's auroras are the warning lights of this system. Auroras happen when charged particles crash into an atmosphere and excite atoms and molecules, forcing them into higher energy states. The atmosphere then emits light as it relaxes back to lower energy states, releasing photons with characteristic colours and wavelengths. On Jupiter, much of that light is in ultraviolet and infrared, beyond human vision, because the dominant emissions come from hydrogen and its ions. Yet the physics is the same: energy in, photons out. On Earth, auroras are mostly powered by solar wind disturbances. On Jupiter, the Sun contributes, but it is not the main engine, and that changes the meaning of the glow. Jupiter's rotation and internal magnetospheric currents can drive auroras even when the solar wind is calm. That means the aurora is not just space weather, a temporary response to a storm. It is an expression of the planet's internal power budget, written into the sky. That difference matters because it means the violence is built in. The aurora is not only a response to external weather, and it does not need a trigger to exist. It is a symptom of a machine that runs continuously, because the planet keeps spinning and the magnetosphere keeps trying to enforce corrotation. When the solar wind intensifies, the system can flare brighter, and the ovals can shift. When the solar wind relaxes, the system still glows, because the engine never turns off. Visually, Jupiter's poles are crowned with luminous rings and shifting patches, like a restless halo pinned to the planet's axis. The main oval traces a persistent loop around each pole, like a neon latitude line drawn by invisible currents. Smaller arcs flicker and slide, appearing and fading as conditions change, and some emissions pulse with a rhythm that hints at rotating structures. The light is a map, and the map is alive, responding to currents you cannot see. Observations turn those lights into diagnostics. Hubble has watched Jupiter's ultraviolet auroras pulse and shift, revealing changing currents and particle precipitation over hours and days. In ultraviolet images, the ovals can brighten, ripple, and fragment, and the polar regions can show complex swirling structures. Those changes correspond to variations in magnetospheric dynamics and solar wind input, even when the connection is indirect. The telescope becomes a remote sensor for an invisible machine, watching the output to infer the wiring. Juno has flown through auroral regions, measuring fields and particles directly, confirming the system's intensity with in situ evidence. It samples the electric and magnetic fields, counts particles, and records the wave environment, building a physical profile of the acceleration zones. Those measurements connect the glowing aurora to the currents that drive it, making the link more than a theory. They also reveal how complex the acceleration processes can be, with multiple pathways operating at once. The aurora is not one mechanism, but a family of mechanisms. Auroras also reveal structure. There are main ovals tied to corrotation enforcement, footprints connected to moon interactions, and polar emissions linked to complex dynamics. Each feature is a map of energy transfer, not a decoration, and each has a different driver. The footprints are especially telling, because they show that moons can electrically couple to Jupiter through magnetic field lines. A moon can act like an obstacle in the flow, generating currents that trace back to the planet and light up the atmosphere like a signature. The magnetosphere has its own geography, and it shapes risk. The bow shock marks the first collision with the solar wind, where order becomes turbulence. The magnetopause marks the border where Jupiter's field dominates, and where entry means new rules. The magnetotail stores energy, and can release it in bursts, changing conditions far from the planet. Between these landmarks lie regions with different particle densities, energies, and wave activity. A spacecraft crossing them experiences a sequence of environments, not one uniform zone. Those bursts can resemble substorms, but scaled up. Stored magnetic energy can be converted into particle acceleration and heating, and the conversion can be sudden. The system can reconfigure quickly, changing particle fluxes and exposing spacecraft to unexpected conditions, even along a planned trajectory. In Earth's magnetosphere, similar processes can trigger auroral substorms and energetic particle injections. At Jupiter, the same physics plays out in a larger, more energetic arena, where the stakes for hardware are higher. This is where the chapter's fear becomes practical. Radiation and charging are not abstract when you build hardware that must keep thinking in a hostile environment. Electronics can be upset by single energetic particles, because a tiny deposit of charge can mimic a real signal. A single ion can flip a bit in memory, trigger a false command, or corrupt a sensor reading. When the particle environment is intense, these events become frequent enough to shape mission design. The environment becomes part of the engineering team, and it is not cooperative. Materials can degrade, sensors can saturate, and computers can reset or fail. High-energy particles can damage semiconductor lattices, reducing performance over time, and they can also create trapped charge in insulating layers. Optical surfaces can darken, and detectors can accumulate noise, slowly losing sensitivity like eyes adjusting the wrong way. Even wiring insulation can suffer, especially when charged particles and ultraviolet radiation work together to break chemical bonds. Around Jupiter, time itself becomes a threat multiplier, because dose accumulates whether you're ready or not. Spacecraft also accumulate charge in plasma environments. Different surfaces charge differently, creating voltage differences across the vehicle, and those differences can be sharp at edges and seams. Sunlit areas emit electrons through photoelectric effects, while shadowed areas can collect electrons from the plasma, creating an imbalance. Insulators hold charge longer than conductors, so patches of the spacecraft can behave like separate electrical islands. These differences can build until the spacecraft becomes a charged object in a charged sea. Discharges can occur, producing arcs that damage components and corrupt data. An arc is a sudden equalization of potential, a miniature lightning strike across a gap, and it can happen faster than any protective software can respond. It can pit surfaces, inject noise into circuits, and create transient currents that confuse instruments at the worst moment. Engineers fear arcs because they are fast, unpredictable, and sometimes catastrophic. Jupiter's plasma environment makes them more likely, because the charging sources are persistent and the trapped particle flux is high. Jupiter's magnetic environment increases these risks by trapping and energizing particles. It also increases them by being large and dynamic, so the hazard begins earlier than intuition suggests. A mission can be in trouble long before it reaches the cloud tops, simply because it has crossed into the domain where particles are stored and accelerated. The first encounter with the Empire can happen millions of kilometers away, when Jupiter is still a bright point. By the time Jupiter looks close, the environment may already be working on the spacecraft. Engineers treat Jupiter like a high-radiation laboratory with moving walls. Shielding becomes a mass trade because every kilogram of protection costs fuel and payload, and those costs cascade through the mission. Aluminum and specialized materials can reduce radiation, but they cannot eliminate it, especially at the highest energies. Some particles are so energetic that practical shielding only slows them, and slowing still means damage. Design becomes a negotiation with physics, and physics does not bargain. Trajectories are chosen to limit time in the worst regions because exposure is cumulative. Radiation dose is not just about intensity, but about duration, and that is a cruel arithmetic. A brief pass through a harsh region may be survivable, especially if systems are powered down or protected. A long stay can be fatal to electronics and instruments, even if nothing dramatic happens in a single moment. Mission planners therefore think in terms of time budgets, not just distances, and every orbit becomes a compromise. Time limits become part of the design language. Instruments are hardened, redundancy is added, and sensitive systems are placed behind protective vaults, because survival is a probability, not a promise. Even then, the plan often assumes degradation, because the environment can be harsher than predicted or can change unexpectedly. A spacecraft can be built to tolerate a certain dose, but the environment can still surprise. Jupiter does not sign contracts, and it does not care about schedules. Juno is a case study in this logic. It uses a titanium radiation vault to protect key electronics, sealing them inside a dense shell like a safe inside a storm. Titanium is dense enough to reduce particle flux, and the vault encloses the most vulnerable systems, including the main computer. Juno also uses radiation-hardened components and careful operational planning because shielding alone is never enough. Every subsystem is designed with the environment in mind, from data handling to instrument duty cycles. It follows a polar orbit that minimizes time spent in the most intense equatorial belts, because geometry can be as important as shielding. The worst radiation belts tend to concentrate near the magnetic equator, where trapped particles drift and accumulate in long-lived populations. A polar orbit slices through quickly, reducing exposure while still allowing close passes over the poles and near the planet. Juno dives in, collects data, and escapes outward again, repeating the pattern like a cautious swimmer touching a whirlpool. The orbit is a survival strategy, written into celestial mechanics. But even a careful trajectory cannot avoid the magnetosphere itself. Entering Jupiter's magnetic domain is like stepping into a running machine, because the machine is driven by rotation and fed by plasma sources. The field is already moving plasma, already generating currents, already storing particle populations in belts and layers. There is no off switch to wait for, and there is no quiet season that lasts. The Empire is always operating, and it operates on anything that enters. This is why the magnetosphere feels like an empire. It has borders, internal circulation, and energy sources, and it imposes rules on motion inside its reach. It also has consequences for anything that crosses into it, whether that intruder is a moon, a dust grain, or a spacecraft. The Empire does not need to notice you to affect you, and it does not need to aim. It only needs to keep doing what it does, and that is enough. The comparison to Earth clarifies the threat. Earth's magnetosphere is a shield that can still produce danger during storms, and we have built much of our technology to tolerate it. Jupiter's magnetosphere is a shield that also acts like a power plant, forcing rotation into space and turning plasma into a weapon. The same concept, magnetic protection, splits into two outcomes when scale and rotation change. One is mostly shelter, the other is sustained acceleration, and acceleration is what fills belts with teeth. The word weaponized does not imply intention. It describes function and effect at scale, the way a river can be weaponized by a dam without the river choosing anything. Jupiter's magnetosphere can shred electronics because it traps and accelerates particles so efficiently, and because it keeps doing so continuously. It turns ordinary plasma into a persistent radiation environment, and persistence is what breaks systems. It turns distance into exposure, and exposure into failure, even for careful missions. The magnetosphere also connects Jupiter to its surroundings. It interacts with the solar wind, but it also interacts with the planet's moons through magnetic coupling and shared plasma environments. Those connections create currents that can heat atmospheres, sputter surfaces, and supply more plasma, feeding the machine that then feeds back into the moons. The coupling is a two-way exchange, and it leaves signatures in auroras and particle populations. Jupiter is not isolated inside its own field. It is networked to its neighborhood, and the network carries energy. So the central question deepens. What makes Jupiter terrifying, Guess, is not only what it does locally, near the clouds and storms we can admire. It is how far its influence extends, and how it turns space into part of its operating system, with rules enforced by fields. When we say space around Jupiter, we're not describing emptiness. We are describing a controlled volume where forces dominate motion and where matter is processed into hazard. That first impression is the lie this documentary is built to break. Jupiter's calm light hides a boundary that begins far from the planet, where no cloud gives you warning. The danger starts in invisible structure, not invisible weather, and it begins before you feel arrived. The clouds are dramatic, but they are not the first hazard, and they are not the first test. The first hazard is the field you cannot see, and the currents it organizes. To feel the threat, follow one charged particle approaching Jupiter. It arrives with the solar wind, fast and indifferent, one speck in a vast outflow from a star. It carries kinetic energy from the sun's expanding atmosphere, and it has no awareness of planets or missions. In the darkness between worlds, it is just one member of a vast flow, drifting through magnetic spirals carried by the wind. Then it meets Jupiter's influence, and the rules tighten. At the bow shock, it is slowed and redirected. Then it crosses into a region where Jupiter's field takes control. The particle's motion becomes less like a straight-line flight and more like a forced dance, constrained by geometry it cannot escape. Turbulence at the shock can scatter it, changing its direction and energy, and some particles are reflected back outward. Downstream, magnetic fields become more ordered, and the planet's rotating structure asserts itself. The particle is no longer in the solar wind's domain, and it begins to behave like a captive. The particle begins to spiral along a field line. It bounces between hemispheres, guided by magnetic mirrors near the poles, and each bounce carries it through regions of different density and wave activity. It drifts around the planet, and each loop gives the system another chance to energize it, or to scatter it into a new orbit. The motion is repetitive, and repetition is what makes acceleration effective. A single pass might do little. 1,000 passes can transform it into something lethal. Waves in the plasma can transfer energy to the particle. These waves are oscillations in electric and magnetic fields, generated by instabilities and currents, and they can range from slow undulations to rapid, whistling modes. When a particle's motion resonates with a wave, energy exchange becomes efficient, like a swing being pushed at the right moment. The particle can be pushed to higher speeds, and higher speeds mean higher radiation hazard. In plain language, the magnetosphere can pump the particle again and again. Electric fields tied to corrotation can accelerate it further. As the system tries to enforce rotation, it sets up potential differences across regions of plasma, and those potentials can span enormous distances. A charged particle moving through those fields gains energy, like a bead sliding down an electric slope, and the slope can be steep. Around Jupiter, those slopes can be relentless, because the planet's rotation keeps supplying power. The acceleration does not need a storm, it needs only spin. What began as ordinary solar wind becomes a more dangerous population, trapped in a space that behaves like an accelerator ring. The particle's energy increases, and its ability to damage electronics increases with it, because higher energy means deeper penetration and more ionization along its path. It can penetrate deeper into materials, create more secondary particles, and trigger more disruptive events in sensitive components. The field does not merely trap, it processes, and it processes at scale. As more particles are captured, the belts grow denser and harsher, and the system becomes a reservoir of radiation. The magnetosphere becomes a waiting room of energetic matter, ready for anything that enters, whether it intends to study Jupiter or merely pass by. The invisible monster is not the field alone, but what the field can hold and maintain over time. A magnetic field is geometry and force. A radiation belt is that geometry filled with energetic matter, and the filling is what bites. This is why the chapter's title matters. The monster is invisible because magnetism does not glow, and plasma can be too thin to see even when it is dangerous. It reveals itself only through consequences, through auroral light, through damaged electronics, through instruments overwhelmed by particle counts and noise. If you could see the trapped particles, Jupiter would look surrounded by a storm of needles, a halo of motion and impact. Instead, it looks serene, and serenity becomes misdirection. In the next chapter, we move from the borders to the furnace. We quantify the radiation belts and the doses they deliver, translating glow and theory into numbers that engineers fear. We see how Jupiter turns magnetism into a kill zone that can end missions quickly, sometimes faster than a timeline can tolerate. The Empire's lights will become numbers, and the numbers will become limits. The invisible monster will gain a measurable weight. For now, the key fact stands. Jupiter's true size is not its disk, but its magnetic reach, and that reach is the first thing you enter. The planet looks peaceful from Earth because its most dangerous features do not reflect sunlight, and they do not cast shadows. They are written in fields, currents, and trapped particles. They are written in physics, and physics is always on. And once you cross that invisible boundary, the rules change. Space is no longer empty. It is occupied by a rotating, electrified empire that does not care what you built, or why you came, or how carefully you planned. Jupiter's magnetic empire is not just wide. It is packed with trapped radiation that turns nearby space into a kill zone. From far away, the planet looks serene. Striped clouds, a slow-turning marble, sunlight sliding across its bands. Through a telescope, the disk is almost painterly, with soft edges and pastel zones that seem to promise calm. Up close, that calm surface hides a region where space itself becomes hostile, because the emptiness is filled with fast, charged shrapnel. The danger is easy to misunderstand because it has no obvious shape. There is no glowing ring you can photograph like Saturn's, and no single boundary you can draw with confidence. Instead, the threat is statistical and relentless, an invisible rain of particles that strikes, penetrates, and accumulates. Radiation belts are regions where energetic electrons and ions are trapped by magnetic field lines. The magnetic field is invisible, but it acts like rails that guide charged particles, forcing them into repeating paths that can last for days or months. In practice, those rails are curved, twisting structures that fill a vast volume, and they impose order on particles that would otherwise fly away. A trapped particle does not simply circle Jupiter once and leave. It spirals around a field line, it bounces between the northern and southern magnetic hemispheres, and it drifts sideways around the planet as the field curves. That motion is not a metaphor, it is a measurable choreography that spacecraft instruments can reconstruct from particle counts and directions. The spiral is the tightest motion, driven by the Lorentz force as a charge moves through a magnetic field. The bounce is slower, caused by magnetic mirroring, because field strength increases toward the poles and reflects particles back. The drift is slower still, and it depends on gradients and curvature in the field that push different charges in different directions. That three-part motion, spiral, bounce, drift, creates confinement, and confinement creates opportunity. If a particle stays trapped long enough, it can be accelerated again and again, building energy the way a repeated push builds a swing. The longer the particle remains in the system, the more chances it has to meet the next electric field, the next wave, the next energizing event. Earth has the Van Allen belts, and they already threaten satellites and astronauts. Those belts were discovered early in the space age, and they quickly became a practical lesson in how near-Earth space is not uniformly safe. When Explorer 1 carried a Geiger counter in 1958, the instrument went strangely quiet at times, not because radiation vanished, but because it was overwhelmed. Engineers learned to harden electronics, to plan orbits, and to accept that certain regions deliver higher dose. Even so, Earth's belts remain a constant constraint for spacecraft that cross them repeatedly. Operators schedule sensitive activities, like detector calibrations and high-voltage operations, around the times when the radiation environment is least punishing. Jupiter's belts are the same basic phenomenon, scaled into a different category of hazard. The underlying physics is familiar, but the numbers are not. Intensity, energy, and spatial extent all rise sharply. The planet's magnetic field is stronger than Earth's, and its magnetosphere is fed and powered in ways Earth simply is not. The difference is not subtle, and it is not a marketing exaggeration. At Jupiter, particle fluxes and energies jump by orders of magnitude, and survivability becomes a time budget. You do not ask, is it dangerous? Because the answer is already yes. You ask, how long can we stay functional here, and what do we sacrifice to buy minutes? Flux is the rate at which particles strike a surface, and energy determines how deeply they penetrate. When both rise together, shielding becomes less effective, and even brief exposure can dominate a mission's total lifetime dose. A thin layer that works in Earth orbit can become almost symbolic at Jupiter, because the particle energies are simply too high. A belt is not a solid ring you can point at and avoid. It is a set of overlapping populations with gradients, injections, and wave activity that change with conditions. One region may be dominated by electrons, another by heavier ions, and their intensities can vary with time, local time, and magnetic geometry. The belts also have structure in latitude and longitude, because Jupiter's magnetic field is not perfectly centered or perfectly symmetric. That tilt and offset create regions where the radiation is locally worse, hotspots that sweep past as the planet rotates. A spacecraft can therefore experience a repeating rhythm of hazard, as if the planet's rotation is turning a dangerous beam through space. To understand why Jupiter is so dangerous, we have to explain how particles become that energetic. Trapping alone stores particles, but acceleration is what sharpens them. In other words, the belts are not just a warehouse. They are an active factory where energy is continually added. In the simplest picture, a magnetic field is a bottle, and the belts are what happens when the bottle is constantly shaken and powered. Jupiter does not merely confine particles, it repeatedly pumps energy into them. That pumping is not occasional, and it is not subtle, because the planet has a powerful internal driver. Jupiter's fast spin is the first amplifier. The planet rotates in about 10 hours, and that rotation forces the magnetosphere to try to corrotate. 10 hours is fast for a world that large, and it means the magnetic field is sweeping through space at tremendous speed. Corrotation is not a gentle suggestion, because Jupiter's magnetic field is strong and far-reaching. Plasma embedded in that field feels an electromagnetic tug, and the system tries to drag charged material around with the planet. The farther out you go, the harder this becomes, because corrotation demands higher and higher linear speeds. Corrotation creates large-scale electric fields in the plasma. Those fields do work on charged particles, pushing them to higher energies as they move through the system. In plain terms, the rotating magnetic field acts like a moving conveyor, and particles gain energy as they are forced to keep up. In simple terms, Jupiter's rotation acts like a generator connected to space. It converts rotational energy into particle energy, continuously, not only during solar storms. The power source is the planet's spin, and the wiring is the magnetic field that threads through the plasma. That continuous power matters, because it means the belts do not need rare events to remain dangerous. Even on a quiet day at the Sun, Jupiter's internal engine keeps accelerating and circulating charged particles. The system can therefore maintain high-energy populations for long periods, building a persistent hazard rather than a transient one. The electric fields associated with corrotation also set up currents, and those currents couple different regions of the magnetosphere. When conditions shift, energy can be redistributed quickly, like tension moving along a stretched cable. That coupling is why a change far from the planet can still alter radiation conditions closer in. Wave-particle interactions provide another acceleration pathway. Plasma waves can resonate with particle motions, transferring energy efficiently when timing and geometry align. Resonance is the key word, because the exchange becomes strong when the wave's rhythm matches the particle's natural frequencies. A plasma is not just a gas of charged particles, it is a medium that supports collective behavior. It can ring with electromagnetic and electrostatic waves, and those waves can act like moving stair steps for particle energy. Some waves are driven by instabilities, some by injections, and some by the constant stresses of rotation and transport. Some of these waves scatter particle pitch angles, changing how they bounce between hemispheres. Others push energies upward, building populations of relativistic electrons. A particle can therefore be both endangered and empowered by waves, because the same processes that scatter can also accelerate. Pitch angle is the angle between a particle's velocity and the magnetic field line, and it decides a particle's fate. If the pitch angle shifts too far, the particle can plunge into the atmosphere and be lost, but if it stays within a safe range, it remains trapped. That safe range is often described as a loss cone, a geometric window that leads downward into the planet. That scattering can sound like a safety valve, yet it can also increase hazard near spacecraft altitudes. By reshaping the distribution, waves can concentrate particles into regions where a passing probe takes the brunt. The belts are therefore dynamic, not only in intensity, but in how the particles are arranged in space. Relativistic means the electrons are moving close to light speed. At those energies, they penetrate shielding more effectively and cause deeper, more complex damage. They also carry enough energy that a single impact can matter, because it can trigger secondary effects inside materials. Relativistic electrons also behave differently in materials because they generate cascades of secondary radiation. When they strike shielding, they can produce bremsstrahlung X-rays, new radiation created by the act of trying to stop the original particle. The spacecraft's own protective layers can therefore become a source of additional radiation, which is a cruel twist of the physics. So the problem is not only the incoming particle, it is the chain of interactions that follows, where one energetic electron can create a spray of effects inside the spacecraft's own structure. Designers have to think in layers: primary particles, secondary photons, and the way both deposit energy and sensitive components. The belts are also fed by external input from the sun. Solar wind disturbances can inject fresh particles and compress the magnetosphere, raising intensities in short bursts. Even at Jupiter's distance, the solar wind still carries shocks and pressure changes that can jolt the system. When the solar wind pressure rises, Jupiter's magnetic boundary can be pushed inward, squeezing the trapped populations. Compression increases energy through adiabatic effects, because the same particles occupy a smaller magnetic volume and gain energy as conditions tighten. It is like squeezing a spring. Work is done, and the stored energy rises. Those solar-driven changes can be sudden, and they can arrive with little warning at Jupiter's distance. A spacecraft that is safe one orbit can find itself in a harsher environment on the next pass, simply because the solar wind has shifted. The belts respond not only to local processes but also to the broader space weather environment. But Jupiter's worst radiation is not only a solar story, it is also a moon story, and the key moon is Io. In the Jovian system, moons are not passive ornaments. They are active participants in the magnetospheric machine. Io is the most volcanic world we know. Its eruptions loft sulfur dioxide and other material into space, where sunlight and collisions strip electrons away. The plumes can rise hundreds of kilometers, and they feed a cloud that spreads along Io's orbit like a trail. The volcanism is powered by tides, not by internal radioactivity alone. Jupiter's gravity flexes Io like a stress ball, and the repeated kneading heats the interior until rock behaves like a slow, glowing fluid. Resonances with neighbouring moons keep the orbit slightly eccentric, so the flexing never fully relaxes. In telescopic images, Io's surface looks mottled and stained, as if painted with sulphurous pigments. Up close, it is a landscape of fresh deposits and active vents, continually resurfaced by eruptions that never truly stop. The colours are not decorative, they are chemistry, frozen and reworked by heat and radiation. Once ionized, that material becomes sulfur and oxygen ions. Jupiter's magnetic field captures them, and the planet's rotation forces them into a dense plasma torus. The ions are heavy compared to electrons, and their presence changes how the magnetosphere carries mass and current. Ionization happens through ultraviolet sunlight, through impacts with existing plasma, and through charge exchange processes. The result is a steady conversion of neutral volcanic gas into charged particles that the magnetosphere can grab. Over time, that steady supply becomes a defining feature of Jupiter's inner space environment. A plasma torus is a donut-shaped ring of ionized gas around the planet centered near Io's orbit. It is a reservoir of mass that the magnetosphere must carry. Instruments have detected it as a region of enhanced density and characteristic emissions, a faint signature of charged matter in motion. Visually, you can imagine a faint glowing loop encircling Jupiter, not as a solid band, but as a fog of ions. It is tenuous by Earth standards, yet enormous in volume, and it becomes a key ingredient in Jupiter's radiation chemistry. In some wavelengths, it would look like a delicate halo, but it is anything but gentle. This is how a moon loads a planet's space environment. Io supplies raw material, and Jupiter's electromagnetic engine processes that material into radiation. It is a pipeline from geology to plasma physics, linking volcanic vents to energetic particles thousands of kilometers away. The loading has consequences. More plasma increases currents, drives instabilities, and provides more particles that can be accelerated and redistributed inward. When you add mass to a rotating system, you change its balance, and the magnetosphere responds by reorganizing how it transports energy. When the magnetosphere is mass-loaded, it cannot corrotate perfectly everywhere, and that mismatch creates additional electric fields. Those fields can drive transport, moving particles across magnetic shells and feeding the inner belts. The system becomes a set of coupled flows, where particles migrate inward and outward depending on conditions. As particles move inward, magnetic field strength rises, and conservation effects can increase their energy. The environment becomes harsher closer to the planet. The inner regions are therefore not just nearer in distance, they are deeper inside the magnetic machine. One of the key ideas is adiabatic invariance, a formal way of saying that certain aspects of a particle's motion are preserved if changes are gradual. As a particle drifts inward to stronger magnetic fields, its gyration energy can rise, turning transport into acceleration. The process is subtle in description, but brutal in consequence, because it upgrades ordinary particles into dangerous ones. The result is a set of belts that are not merely intense. They are maintained by a system with internal fuel, internal power, and constant rotation. Jupiter does not need to wait for the Sun to deliver energy, because it is already spending its own rotational energy every second. Jupiter is therefore not just a target you visit, it is a machine you enter. Its belts are the output of a coupled system: rotation, magnetic field, plasma sources, and waves all feeding back on one another. That coupling is why the belts are persistent, structured, and difficult to predict in detail. Now we translate the physics into danger that matters to bodies. Ionizing radiation breaks chemical bonds and damages DNA, and the damage accumulates with dose. The word ionizing is the warning label, because it means the radiation has enough energy to change matter at the atomic level. Ionizing radiation is defined by its ability to knock electrons off atoms and molecules, creating ions and reactive fragments. In living tissue, that means broken strands of DNA, altered proteins, and chemical pathways that can be disrupted in seconds. Much of the injury is indirect, because ionization also creates free radicals that attack nearby molecules. High doses delivered quickly overwhelm cellular repair. Tissues with rapid cell division are hit first, and whole body exposure becomes life-threatening fast. The biology is not mysterious, but it is unforgiving, because damage scales with both intensity and time. The body does have repair mechanisms, and cells can often correct damage if the rate is low enough. The problem near Jupiter is that the rate can be so high that repair becomes a losing race. When too many breaks occur at once, the probability of misrepair rises, and the consequences cascade through organs and systems. Near Jupiter's belts, the key point is time. Unshielded exposure in the wrong region would deliver a lethal dose in minutes, not days. The phrase "in the wrong region" matters, because the belts have gradients, yet the peaks are severe enough to define the overall risk. That statement is not meant to be sensational, because it is a straightforward consequence of measured intensities. In the most intense zones, the environment is closer to a particle accelerator's byproducts than to the gentle background radiation we live with on Earth. The comparison is about dose rate, the speed at which energy is deposited in tissue. We do not need gore to make this real. The numbers alone force the conclusion that humans cannot simply fly through and hope for the best. Even a well-planned trajectory would require heavy shielding, careful timing, and strict limits on time spent near the strongest belts. Even if a crew could tolerate a brief spike, the mission would still face cumulative risk, because repeated passes add up. A habitat that is safe for a short transit might not be safe for a campaign of orbits and close flybys. The difference between a dash and a residency becomes the difference between plausible and impossible. Shielding helps, but shielding is mass, and mass is mission cost. Even thick shielding has limits against the most energetic electrons and secondary radiation. The most effective protection often involves not only material, but also geometry, because you want to reduce the angles through which particles can reach critical areas. A useful mental image is a storm of bullets where some are stopped by a wall, yet the fastest create splinters behind it. High-energy electrons can generate X-rays in shielding, and those X-rays can penetrate deeper than expected. The wall still helps, but it changes the character of what gets through. So designers balance materials, thickness, and geometry, often using layered approaches. They also place the most sensitive electronics deep inside the spacecraft, using tanks, structure, and instruments as additional shielding. Even propellant and water can become protective mass, which is one reason mission layouts are so carefully negotiated. Radiation is also not only a health issue, it is an electronics issue, a materials issue, and a data integrity issue that can end missions quietly. A spacecraft can look fine from Earth, transmit a carrier signal, and still be slowly losing its ability to measure the world. Spacecraft are built from semiconductors, insulators, optical coatings, and delicate detectors that assume stable behavior. Radiation turns that stability into a probabilistic gamble, where rare events become common, and common events become constant. The environment does not need to hit the spacecraft in a dramatic way, because it can erode performance one defect at a time. A single energetic particle can flip a bit in memory. That is a single event upset, and it can turn a correct command into a wrong one. The frightening part is that the particle does not need to break anything physically, because the disturbance can be purely electrical. In a modern spacecraft, memory is everywhere, from instrument buffers to attitude control tables. A flipped bit can be harmless, or it can be catastrophic, depending on where it lands and whether error correction catches it. That is why spacecraft software is written with paranoia in mind, expecting that the hardware may lie. A particle can also trigger latch-up in a circuit, creating a short that draws destructive current. If protection fails, a component can burn out instantly. Latch-up is not a slow decline, but a sudden failure, and it can happen during a single pass through a harsh region. Latch-up is especially dangerous because it can masquerade as a normal electrical load for a moment. The system may not realize something is wrong until heat rises, current spikes, and the damage is already permanent. At Jupiter, where particle rates are high, that moment can arrive more often than designers would like. Detectors degrade as radiation damages semiconductor lattices. Noise rises, sensitivity falls, and measurements become less trustworthy over time. The physics is microscopic: displaced atoms, trapped charges, altered band gaps. Yet the consequence is macroscopic, because the instrument's view of the world becomes foggier. A camera sensor, for example, can develop hot pixels and streaks, because defects act like tiny false signals. Over months, those defects accumulate, and the clean image the mission promised becomes harder to extract from the background. Engineers can sometimes correct the damage in software, but correction is never perfect, and it costs precious time. Solar panels darken as energetic particles damage their structure. Power output drops, and the spacecraft loses the margin it needs for heaters and transmitters. The effect is like a slow dimming, not because sunlight changes, but because the panel's ability to convert light into electricity is being degraded. That loss of margin is not abstract at Jupiter, where sunlight is already weak compared to Earth. If power falls, you may have to choose between keeping instruments warm, keeping communications stable, or keeping the spacecraft oriented safely. Those choices can determine whether the mission continues as planned or limps onward with reduced capability. Insulators accumulate charge, and differential charging can lead to discharges. A tiny arc can corrupt data, reset systems, or damage surfaces. The arc is microscopic, yet it can be violent enough to pit a surface or inject noise into a sensitive line. Charging is a subtle threat because it depends on the local plasma environment and on spacecraft geometry. Two nearby surfaces can build different potentials, and when the difference becomes large enough, the discharge is sudden and violent at a microscopic scale. The spacecraft is, in effect, a complex shape moving through a charged sea, and small design details can matter. The cruel part is that much of this damage is cumulative. A spacecraft can function today, then fail tomorrow, because the dose budget has been spent. The failure can look like bad luck, yet it is often the final step of a long, invisible accounting. Cumulative damage is why radiation feels like corrosion, even though it arrives as invisible impacts. Each particle strike is small, but the long-term effect is a steady drift toward failure. The mission may survive a dramatic event, then be undone by the quiet accumulation that follows. This is why mission planners talk about total ionizing dose and dose rate. Dose rate sets immediate risk, and total dose sets the mission's lifespan. One is about spikes and upsets, and the other is about slow degradation that cannot be reversed. Total ionizing dose is essentially the integrated energy deposited in materials over time, and it changes how components behave. Dose rate, by contrast, can trigger immediate upsets and overload protective systems during a single intense pass. At Jupiter, both matter, because the environment can be both persistently harsh and suddenly worse. Spacecraft time at Jupiter is finite. Every hour in the belt spends an invisible currency that cannot be earned back. That currency is measured in gray, rad, and component test limits, yet it feels like a countdown that ticks even when nothing seems to be happening. That currency shapes everything, from how close you dare to fly to how long you keep a detector exposed. It also shapes the emotional rhythm of operations, because each close approach is both a scientific opportunity and a survival test. Teams learn to treat Perijove like a storm season, with preparations, procedures, and contingency plans. Galileo proved that reality in the harshest way. It orbited Jupiter for years, but radiation repeatedly hammered its systems and corrupted its data. The mission was heroic, yet it was also a reminder that Jupiter does not care about human schedules or budgets. Galileo arrived in the mid-1990s when spacecraft electronics were less hardened than many modern designs. It carried remarkable instruments for its time, yet it entered an environment that treated those instruments like targets. The spacecraft's long tour of the system meant repeated crossings, and repeated crossings meant repeated damage. Its cameras and electronics suffered anomalies, resets, and noise. Engineers learned to expect glitches as normal operations inside Jupiter's furnace. When a subsystem misbehaved, the question was often not, why did it happen, but how many more times can it happen before we lose control? Some images returned with streaks and speckled artifacts, where energetic particles struck the detector during an exposure. Some data streams were interrupted, and some subsystems required repeated resets, because the environment kept pushing them out of nominal behavior. The artifacts became a kind of signature, a reminder that the camera was not only seeing Jupiter, but being struck by it. Galileo's struggles were not a failure of engineering effort. They were a measurement of the environment, delivered through broken pixels and lost bits. In deep space, the boundary between instrument problem and scientific data can blur, because the environment itself is what you're trying to understand. In a sense, the spacecraft became an unintended radiation experiment, mapping danger by the pattern of its own wounds. Each anomaly told a story about where the belts were strongest and how unpredictable the particle populations could be. Those lessons did not stay in reports, because they shaped the next generation of mission design. Juno was designed with those lessons in mind. Its core electronics sit inside a titanium radiation vault to reduce exposure to the most damaging particles. The idea is straightforward. If you cannot make the environment gentle, you make the spacecraft's most vulnerable parts harder to reach. Titanium is dense enough to help, and it is structurally practical for a spacecraft that must also survive launch loads. The vault is a literal box around the brain of the mission, built to reduce dose and to stabilize the environment for sensitive components. Visually, it is like a safe embedded inside the spacecraft, a heavy core surrounded by the rest of the vehicle. The vault is not a magic shield. It is a compromise that buys time, lowering dose enough for the mission to complete key objectives. The best shielding is still imperfect because the highest energy particles and the secondary radiation they create can still penetrate. Even inside the vault, some radiation gets through, and secondary radiation can be created in the shielding itself. The goal is not invulnerability, but a manageable rate of damage, slow enough that the mission can finish before the clock runs out. That is the realistic standard at Jupiter, and it shapes every engineering decision. Juno's orbit is also a survival strategy. A polar trajectory reduces time spent in the worst equatorial belt regions, where trapped populations are densest. The choice is geometric and strategic, because the belts are not uniform, and the equatorial region is where many particles spend most of their drift motion. The densest belts tend to concentrate near the magnetic equator, where many trapped particles spend much of their drift motion. By approaching over the poles, Juno threads a path that still crosses hazardous regions, but it avoids lingering in the deepest, most saturated zones. It is not a safe route, but it is a survivable one. It dives close, collects data, then escapes outward again. The mission is built around short exposure windows, not continuous presence. That rhythm, approach, measure, retreat, turns each close pass into an intense sprint. During each close pass, Jupiter fills the sky, and the spacecraft races through regions where the radiation environment can change rapidly with altitude. The timeline becomes a choreography of measurements: turn on, observe, transmit, then retreat. In visual terms, you can imagine the spacecraft slipping between invisible layers, each one denser with energetic particles than the last. Even with that design, Juno still experiences radiation effects. Instruments can be degraded, and operations must adapt as the environment changes. The mission is therefore not only a scientific campaign, but also a long test of endurance against a hostile particle climate. Engineers watch for rising noise, for unexpected resets, and for subtle shifts in instrument calibration. Over time, they learn which modes are robust and which are fragile. Then they rewrite plans to keep the mission alive. That adaptation is part of the story because it shows exploration as a negotiation with physics. This is where the tension becomes immediate. At Jupiter, science is not only about what you can measure, it is about what you can endure. The planet's magnetosphere becomes an antagonist, not through malice, but through sheer energetic intensity. A spacecraft can be perfectly aimed, perfectly timed, and perfectly programmed, yet still be undone by a particle that arrives at the wrong microsecond. That is the unsettling truth of exploring a radiation furnace. The randomness is not total, because the belts have structure, yet the individual impacts remain unpredictable. Mission planning becomes a sequence of trade-offs. Keep instruments on longer, and you gather more data, but you also burn through dose faster. The trade is not theoretical, because dose is measured, tracked, and compared against component limits like a budget line. The trade-off is not just quantity versus safety, because radiation can also bias the data. A longer exposure might gather more photons from Jupiter, yet it might also gather more particle hits that contaminate the measurement. The result can be a paradox, where more time produces less usable science. So spacecraft carry dose budgets like a countdown clock. Teams schedule instrument shutdowns, safe modes, and protective configurations during the worst passes. They also plan for redundancy, because a component that fails early can sometimes be replaced by a backup path. Those budgets are built from component testing and radiation models, then refined by experience in flight. As the mission proceeds, planners compare predicted dose to measured behavior, adjusting margins as reality reveals itself. The environment becomes a partner in the planning, because it continually forces revisions. Some observations are timed for moments when the radiation is lower. Some instruments are powered down entirely to protect detectors and electronics. The choice can be painful, because every powered down minute is a minute of lost opportunity, yet it can also be the minute that saves the mission. A detector that is off cannot be struck into producing false data, and it cannot be damaged as quickly. Turning instruments off feels like surrender, yet it is often the difference between a mission that ends early and one that keeps returning discoveries. The discipline is part of the craft of operating at Jupiter. Safe mode is not just a software behavior, it is a survival posture, reducing activity to limit vulnerability when the environment becomes too aggressive. When a spacecraft enters safe mode, it is admitting that the storm is winning, at least for the moment. In safe mode, the spacecraft simplifies, shedding non-essential tasks and focusing on staying oriented, powered, and communicative. It is the equivalent of closing shutters in a storm, because the storm is made of particles you cannot see. The goal is to ride out the worst conditions with the least exposure of delicate operations. Every design choice has a cost. More shielding means less payload, less fuel margin, and fewer instruments, and it can still be insufficient at peak energies. The harshness of Jupiter forces these compromises into the open, because there is no free protection. There is also a point where added shielding yields diminishing returns, because secondary radiation begins to matter more. Designers must decide where to place mass, what to protect most, and what risks to accept. The most valuable protection is often targeted, focused on the systems that cannot fail. Even trajectory choices have costs. Avoiding the belts can mean missing key regions, limiting coverage, and stretching timelines beyond what budgets allow. A mission can be made safer by staying farther out, yet it can also be made less meaningful if it never goes where the science is richest. A safer orbit might reduce radiation, yet it might also reduce the frequency of close passes, slowing the accumulation of data. In deep space exploration, time is money, and time is also the finite life of hardware. Jupiter forces teams to spend that life carefully, because the environment is charging interest. Jupiter forces a different definition of exploration. You're not only navigating distance and gravity, you're navigating an invisible storm of particles. The storm is not random weather, but a structured consequence of rotation, magnetic fields, plasma sources, and energy transfer. That storm is shaped by a magnetic field so large it dwarfs the planet. Yet it is also shaped by local sources like Io's torus. The result is an environment that is both global and intimate. Planet-sized structure built from microscopic impacts. Each particle is tiny, yet together they define what is possible near Jupiter. This is also where Jupiter's terror connects back to the central question. The same power that makes Jupiter lethal up close is part of its system-wide influence. The belts are not merely a hazard to visitors, they are part of how Jupiter interacts with its own moons. A magnetic trap this strong reshapes the space around the planet. It affects moons, sputters surfaces, drives auroras, and creates hazards that extend far outward. The system is therefore not a set of separate worlds, but a connected environment where energy and particles move between bodies. Sputtering is a slow sandblasting by energetic particles, and it can alter the chemistry of exposed ice and rock. Over long times, that invisible weathering becomes part of how the Jovian system evolves, because radiation is an agent of change. The surfaces of moons can be modified without a single meteor impact, simply by constant particle bombardment. Jupiter looks peaceful from Earth, because none of this is obvious in reflected sunlight. Up close, the planet is a radiation furnace wrapped in magnetism. The beauty is real, yet it sits behind defenses that are physical, measurable, and indifferent to human ambition. If you could see the belts, the view would change completely. Bright, layered shells of energetic particles surrounding the planet like a luminous hazard sign. The most dangerous regions would not be subtle, and their boundaries would look like gradients of intensity rather than clean edges. You would see a world wearing an invisible armor, and the armor would be alive with motion. The belts are the proof that Jupiter is not a passive world. It is an engine that converts spin and plasma into stored weapon-like particle energy. The word weapon-like is about effect, not intent, because the belts can shred electronics as efficiently as any engineered beam. That energy is stored in motion and in confinement, in particles that have been accelerated and then held in place by magnetic geometry. It is a reservoir that leaks slowly, yet it is replenished constantly, because the engine never stops turning. The system is therefore stable in its danger, even when it is variable in detail, and the belts are not a side feature. They are a gate you must pass through to reach the planet, and they punish every minute you stay. The closer you go, the more the gate tightens, and the more the mission becomes a race against dose. For robotic explorers, that punishment is measured in anomalies and degraded instruments. For human explorers, it would be measured in dose and time, with margins that vanish much faster than intuition expects. The planet's magnetosphere forces humility, because it sets limits that cannot be negotiated away. After the invisible danger of radiation, we finally face the visible face of Jupiter, We move into the atmosphere, where beauty becomes a moving, violent machine. The camera leaves the unseen storm behind and approaches the cloud tops, where colour and motion finally reveal themselves. Yet the lesson remains. Even the most beautiful worlds can be defended by physics, and Jupiter's first defense is invisible. After radiation and magnetism, Jupiter's next threat is visible and constant. The clouds are not scenery. They are the moving skin of a deep heat engine, and they never stop advertising the power beneath. Even in still images, the planet looks busy, like a machine caught mid-cycle, with every belt and swirl implying momentum. From Earth, weather is a thin layer draped over rock and ocean, and it usually feels separate from the planet itself. On Jupiter, weather is the world, because there is no ground to stop it and no shoreline to break it. There is also no familiar boundary layer, where friction quickly slows winds, so motion can persist and organize on enormous scales. When we look through telescopes, we see bands, swirls, and ovals that seem almost painted onto a sphere. Up close, those patterns resolve into a restless three-dimensional fluid, folding over itself in slow waves and sudden eruptions. The band edges are not straight lines but living borders, constantly fraying into curls where instability begins. The camera lingers on the limb, where sunlight skims the atmosphere and turns cloud tops into bright ridges. Shadows fall across stacked layers, and the planet looks less like a ball and more like a deep breathing ocean. The curvature is gentle, yet the vertical relief is real. Cloud towers cast thin, slanted darkness that reveals height without mountains. Jupiter's atmosphere is mostly hydrogen and helium, the same light elements that dominate the Sun. That similarity is not poetic. It is a fossil clue, a reminder that Jupiter formed from the same primordial nebula that built the star. In composition, Jupiter is closer to a failed star than to any terrestrial planet, even though it never ignited. In the early solar system, the young Sun was surrounded by a disk of gas and dust, and the outer regions stayed cold enough for ices to survive. Jupiter grew fast in that environment, pulling in hydrogen and helium before the solar wind could clear the disk away. That timing matters, because once the gas was gone, no later planet could easily become this large. Yet trace compounds matter, because they decide what condenses, what absorbs light, and what we call colour. Methane, ammonia, water vapour, hydrogen sulfide, and complex hazes are tiny fractions, but they dominate the planet's appearance. They also control how energy moves upward, because different molecules trap or release heat at different wavelengths. In practice, trace does not mean unimportant, because a small amount of the right molecule can control an entire cloud deck. A teaspoon of dye can tint a swimming pool, and a few parts per million can tint a planet. The same logic applies to hazes. Thin veils can mute contrasts and soften the entire world's face. Those molecules also act like diagnostic tools, because each one interacts with light in a different way. Some scatter sunlight efficiently, some absorb infrared heat, and some are ripped apart by radiation and rebuilt into stranger compounds. Spectra become fingerprints, and a few missing or shifted lines can reveal temperature, pressure, and vertical mixing. The structure begins with pressure and temperature, not with continents or latitude lines. Higher up, the air is colder and thinner, and clouds form where gases freeze or condense into crystals and droplets. The key is the phase diagram. Each compound has a narrow range where it prefers to become solid or liquid, and Jupiter crosses those ranges with altitude. Deeper down, pressure rises fast and the chemistry shifts as heat forces materials into new phases. Molecules that behave politely near the top begin to collide more often, react more readily, and dissolve into one another under crushing conditions. In simple terms, the deeper atmosphere becomes less like air and more like a reactive, compressed fluid. A useful way to picture it is to imagine descending through a laboratory column, where the thermostat keeps turning up. At each level, the same ingredients behave differently, because pressure and temperature rewrite the rules that matter follows. What looks like a clean layer from afar is, in reality, a zone where competing processes overlap. The top visible deck is often ammonia ice, bright and reflective under weak sunlight. Ammonia condenses at relatively low pressures and temperatures, so it marks higher altitudes where the air is cold enough for crystals to form. Because those particles are small and pale, they scatter light efficiently, which helps make zones look luminous. In close views, ammonia clouds can look like whipped cream spread across the zones, with scalloped edges that reveal active updrafts. Their brightness is not just beauty, it is physics, because reflective particles send sunlight back into space. The brightest patches often indicate fresh uplift, new crystals, newly formed, before they darken or sink. Beneath it sits a layer tied to ammonium hydrosulfide, a compound made from ammonia and hydrogen sulfide. It is a chemical handshake between two trace gases, one that becomes possible only when temperature and pressure cross the right threshold. The result can be a more muted tan layer, which changes how deep we feel we're looking. That handshake changes more than chemistry because it changes particle size, density, and how clouds scatter light. A slightly different crystal can darken a belt, soften a boundary, or make a region look bruised instead of bright. In a world without continents, these subtle optical shifts become the closest thing to geography. Deeper still, water clouds form where temperatures are high enough to keep water vapor aloft until it finally condenses. This is not a gentle drizzle layer, but a region where water can drive violent convection through latent heat release. Water is heavy compared to hydrogen and helium, and that weight adds drama to the buoyancy battle. Latent heat is the hidden energy stored in vapor, and when water condenses, it releases that energy back into the air. That release makes rising parcels more buoyant, which can turn an updraft into a towering self-sustaining engine. The same principle powers terrestrial thunderstorms, yet Jupiter scales it up into columns that can punch through multiple decks. These layers are not neat floors stacked like shelves in a warehouse. They are turbulent regions where updrafts, downdrafts, and mixing smear boundaries, so each deck is a shifting zone rather than a clean surface. A storm can dredge material upward, then leave behind a different chemistry signature after it collapses. Still, the basic sequence matters because it links colour and texture to chemistry and altitude. When we see a bright plume or a dark opening, we're often seeing a change in depth, not just a change in lighting. The atmosphere becomes a cross-section, one that the winds keep rearranging while we watch. Brighter zones often indicate higher, colder clouds that reflect more sunlight back into space. Darker belts can signal deeper views into warmer layers, or different particles that absorb light instead of scattering it. Sometimes a belt darkens because the cloud top's thin, and sometimes because new hazes stain the upper air. The reds and browns can come from photochemical products, altered by ultraviolet light and energetic particles. Sunlight breaks molecules apart, recombines fragments into more complex species, and leaves behind pigments that stain the upper haze. Energetic particles from Jupiter's magnetosphere add to the chemistry, pushing reactions that ordinary sunlight would struggle to drive. Those pigments are sometimes described as chromophores, a term that sounds clinical but means something simple. They are molecules that preferentially absorb certain colours of light, leaving the remaining reflected light shifted toward red and brown. The exact recipe is still debated, which is part of the intrigue. Jupiter shows us the result even when the lab work lags behind. That staining is not uniform and it is not permanent, which is part of the unease. Jupiter's palette is a chemical map, drawn by sunlight from above and heat from below, then erased and redrawn by winds. If the colours can change, then the atmosphere is not merely moving, it is actively transforming. From orbit, the belts look like broad, parallel highways circling the planet. In motion, they ripple and buckle, and their edges fray into curls where the flow becomes unstable and rolls into vortices. The camera can linger on a boundary and watch its spawn eddies, as if the planet is continuously testing its own stability. The visual impression is hypnotic, because the planet carries its own motion lines like a time-lapse photograph. Every band is a record of speed and direction, and every kink is a place where the fluid is arguing with itself. If you could hear it, you might imagine a low, constant roar, an ocean made of gas, never quiet. The heat from below is the key to Jupiter's endless fury, because it never truly stops. Jupiter receives sunlight, but it radiates more energy than it absorbs, and that imbalance is measurable in infrared glow. The planet's effective temperature is higher than sunlight alone can explain, which means something inside is still paying the bill. Infrared instruments see what human eyes cannot, and they reveal a planet that is warm from the inside out. Even on the night side, where sunlight is absent, the atmosphere leaks heat upward like breath in cold air. In thermal maps, some regions glow through thinner clouds, while others look dim where high, cold tops block the view. The extra power is not a mystery source or an exotic fuel burning in the dark. It is leftover heat from formation, plus slow gravitational contraction that still releases energy as the planet very gradually tightens. Jupiter is massive enough that even a tiny shrinkage, spread over time, becomes a steady furnace. In accessible terms, Jupiter is still cooling from being built, and it has had a long time to do it. When the planet formed, impacts and compression stored heat inside a massive body, and the sheer size makes cooling slow. Heat must travel outward through thick layers, and each layer delays the escape like insulation. A big object has less surface area compared to its volume, so it cannot shed heat quickly. Jupiter is the extreme case, a vast reservoir where energy must travel through thick layers before it can escape to space. The planet's size turns time into a resource. Billions of years become a reasonable cooling schedule. Over billions of years, that heat leaks outward through convection and radiation, like warmth seeping from a thick stone after sunset. The process is steady, and the timescales are so long that weather becomes a kind of geology. The clouds are not reacting to a day-night cycle so much as to a deep, slow heartbeat. The second contribution is the Kelvin, Helmholtz mechanism, which sounds abstract but is simple in effect. Jupiter slowly contracts under its own gravity, and as it shrinks by tiny amounts, gravitational potential energy converts into heat. In other words, the planet pays for its glow by settling into itself, almost imperceptibly. It is like a slow squeeze warming a material, except the material is a planet and the squeeze is gravity itself. The contraction is small on human scales, but the energy involved is enormous because Jupiter is enormous. This is not a burst of power, but a long, quiet release, steady enough to matter for weather. This internal heat keeps the atmosphere unstable, and instability is the seed of perpetual motion in a fluid. Warm gas rises, cool gas sinks, and the cycle never ends because the engine never fully shuts down. The rising plumes are not occasional events, they are the planet's default method of transporting energy. Convection is not a seasonal pattern that waits for spring or depends on a particular angle of sunlight. It is a permanent transport system moving energy upward, carrying deep material toward the visible cloud tops. That deep material can include different chemical abundances, so convection becomes both a heat conveyor and a mixing machine. On Earth, sunlight drives most weather, and oceans store and release heat with a delay that shapes seasons. On Jupiter, the interior supplies a large fraction of the budget, so storms are not waiting for daytime. The planet's small axial tilt also weakens seasonal forcing, leaving internal heat as a constant pressure behind the scenes. The planet makes its own weather from within, and that fact changes the emotional scale of the scene. A storm is not a temporary disturbance, it is a symptom of a planet that is still shedding its birth heat. The clouds are an exhaust plume, except the exhaust is cold enough to freeze into crystals. Rapid rotation turns that rising and sinking into bands that wrap the globe like a barcode. Jupiter spins once in about 10 hours, so the Coriolis effect is intense, and the deflection of moving air is immediate. The planet's equator races through space, and the atmosphere inherits that speed as a governing constraint. The Coriolis effect is not a force you can touch, but it is a rule imposed by rotation. Moving air tries to travel straight, yet the spinning planet turns beneath it, so the path curves, and the curve becomes organized flow. On Jupiter, that organization is so strong that it can dominate over the randomizing tendency of turbulence. A parcel of gas that tries to move north or south is twisted sideways, and the sideways motion becomes organized into east-west jets. The faster the spin and the larger the planet, the more strongly rotation shapes the flow. Jupiter's size matters because it allows many jet streams to fit between equator and pole. These jets alternate direction with latitude, creating the familiar belts and zones that even small telescopes can reveal. Instead of a few dominant jets like Earth, Jupiter has many, stacked like lanes with sharp boundaries. Some jets are remarkably stable, while others wobble and spawn waves that travel around the planet. The reason is scale and rotation, but also the way turbulence behaves on a rotating sphere. Energy injected by storms can cascade into large, stable flows, and rotation encourages those flows to align into zonal streams. The result is counterintuitive, chaos feeding order, as if the planet is sorting its own disorder into stripes. On Earth, turbulence often breaks down into smaller and smaller eddies as energy dissipates. On Jupiter, rotation and stratification can push energy the other way, toward larger structures that survive, sharpen, and become long-lived. That is why a storm can seed a vortex, and a vortex can become a landmark. The jets are not gentle winds that merely shift clouds from one place to another. They are high-speed rivers of gas with strong shear at their boundaries, and shear is where adjacent flows slide past each other. In those shear zones, the atmosphere can roll up into wave trains, then pinch off into ovals. Shear breeds turbulence and vortices, because the boundary between fast and slow flow is a place where the atmosphere can tear and curl. Many of Jupiter's most striking ovals are born along these edges, like eddies along a riverbank. Their shapes can be smooth at first, then become ragged as they interact with neighbouring currents. The banding is therefore a visible symptom of deep dynamics, not a superficial paint job. It tells us that Jupiter's atmosphere behaves like a rotating fluid shell, forced by internal heat and constrained by rotation. Each stripe is a compromise between convection trying to move north-south and rotation insisting on east-west order. The stripes are the surface pattern of a planet-sized circulation system, and they hint at depth even when we cannot see it. When a belt darkens or a zone brightens, it can mean the whole vertical column is shifting. A change in cloud opacity can signal a change in upwelling. An upwelling can signal a change in energy transport. Storms form where convection punches through the cloud layers, and the punch is sometimes literal in appearance. Updrafts carry material upward, where it cools and condenses into bright cloud tops that spread like anvils. The anvils can fan out along jet streams stretching into long pale streaks that mark the wind direction. Those anvils can cast shadows on lower haze layers, and the shadows reveal height in a world without mountains. The scene becomes topographic, except the terrain is made of vapor and ice instead of stone. When the sun is low, the shadows lengthen, and the atmosphere briefly looks sculpted, like a relief map in motion. Downdrafts drag drier, warmer gas downward, clearing regions and changing colour by exposing deeper layers. The result is a constantly edited image, where openings appear like windows and then close again. A dark patch can be a hole in the upper cloud deck, revealing a warmer glow beneath, then sealing shut as new clouds form. Lightning proves that some storms reach deep and carry water, which is a critical constraint. Lightning needs charge separation, and charge separation is efficient in strong, wet convection, where ice and liquid collide and exchange charge. Without water, the storm physics becomes harder to reconcile with the observed flashes. In that churning column, particles of different sizes fall or rise at different speeds, and the imbalance helps separate charge. The physics is familiar from Earth, yet the scale is alien, because the storm towers can be immense. The flashes can be bright enough to be seen from orbit, tiny sparks on a planet that dwarfs our world. On Jupiter, flashes have been observed, and their properties match the idea of water thunderstorms far below the ammonia deck. The flashes are not decorative. They are evidence that the convective towers have real vertical reach. Each flash is a brief message from depth, telling us that the lower atmosphere is active and violent. Some flashes illuminate cloud walls from within, briefly revealing texture like ripples on fabric. For an instant, the atmosphere looks solid, and then the light dies, leaving only motion and shadow. The camera can catch that moment and make the planet feel close, even though it remains unreachable. Water matters because it implies depth and power, and because water condenses where pressures are higher. Ammonia can condense higher up, but water condenses deeper, where latent heat release can be enormous and buoyancy can intensify. That deeper condensation level also means the storms tap a larger reservoir of warm rising gas. A water storm is a sign of a deep engine, not a shallow squall, and it changes how we interpret the visible clouds. What looks like a bright blotch at the top may be the cap of a towering column rising from far below. The visible cloud top is a ceiling only in appearance. Beneath it, the column can continue into darkness. Juno's microwave observations add a crucial layer to this story, because microwaves can probe beneath the visible clouds. They pass through upper hazes more easily than visible light, and they are absorbed by certain gases in depth-dependent ways. It is a different kind of vision, less like a photograph, more like an X-ray of weather. By measuring brightness at different wavelengths, Juno infers structure and composition at different depths, almost like taking a set of medical scans. Each channel samples a different layer, allowing scientists to reconstruct a vertical profile. The method is indirect, but the patterns repeat and correlate, which is why the inferences carry weight. Microwaves are especially sensitive to ammonia, which absorbs strongly at certain frequencies. That sensitivity turns ammonia into a tracer, letting scientists follow circulation patterns that would otherwise be hidden behind the planet's bright cloud tops. When ammonia is depleted or enhanced, it can mark upwelling, subsidence, and the pathways of deep circulation. Those data suggest that some features extend far below what we see, and that the atmosphere is not a thin painted shell. It is a deep, layered fluid where storms can reach down tens to hundreds of kilometers, and perhaps more. The implication is sobering. Jupiter's visible beauty is only the upper boundary of a much larger machine. Microwave maps also hint that ammonia is not evenly mixed, which matters for both chemistry and dynamics. If ammonia is being transported by circulation, then the visible cloud patterns are linked to deeper flows that redistribute material. That means a color change may be a circulation change, and a circulation change may be an energy change. That linkage matters because it collapses the distance between surface appearance and interior behavior. Jupiter's colors are not a skin-deep decoration, rather they are a moving cross-section of a system that reaches downward. The planet is showing us its internal plumbing, not with pipes, but with clouds. Lightning, microwaves, and cloud morphology converge on the same conclusion, and the convergence is what makes it persuasive. Jupiter's storms are rooted in depth, and the visible tops are only the upper expression of convective towers below. The more instruments we bring, the more the same story repeats, which is how science earns confidence. At this point, the documentary sphere shifts from invisible radiation to raw planetary power. The threat is not only what particles do to spacecraft, it is what the atmosphere itself does to anything that tries to enter. The clouds are beautiful, yet they are also a warning label written in motion. The Great Red Spot is the emblem of that power, and it is also a historical landmark in astronomy. Long before spacecraft, observers tracked its changing shape through eyepieces, turning a distant smear of colour into a recorded phenomenon. In an era of hand-drawn sketches, the spot became a test of patience, optics, and careful comparison. In the 1600s, early telescopes revealed Jupiter's banding, and astronomers began to suspect the planet was not a static sphere. By the 1800s, consistent observations turned the red spot into a feature with a timeline, not a rumour. That continuity is remarkable. Few atmospheric features in the solar system have a history written by generations. It is an anticyclonic vortex, meaning it rotates opposite to cyclones in its hemisphere's sense of vorticity. It is a high-pressure system in Jupiter's southern hemisphere, spinning with winds that can exceed hundreds of kilometers per hour. In dynamical terms, it is a coherent rotating structure embedded in shear, surviving where intuition says it should unravel. In images, the red spot looks like an eye embedded in the striped face of the planet. Its rim is often brighter and more turbulent, and its interior can show subtle swirls like a storm within a storm. The color is not paint but chemistry, an upper haze stained by photochemical products, constantly renewed and rearranged. The rim is where the wind speed changes sharply with distance, and that gradient acts like a blade. It shreds nearby clouds into streamers, then wraps those streamers around the vortex until they become part of its rotating wall. The boundary is both a barrier and a grinder, keeping the interior coherent while stripping material from the outside. Calling it a storm can mislead, because it behaves like a climate feature rather than a transient event. It has persisted for centuries, observed since at least the 1800s and likely earlier, though the exact identity across time remains debated. The debate itself is telling. Jupiter's atmosphere is active enough to change, yet stable enough to preserve long-lived patterns. On Earth, storms die because they lose heat sources, hit land, or are disrupted by friction and topography. Jupiter removes many of those kill mechanisms, and what remains is a vortex that can recycle energy for astonishing lengths of time. Without continents, the storm never makes landfall, and without a solid surface, it avoids the most efficient braking. There is no solid surface to scrape energy away, and no mountains to disrupt the flow. Friction exists, but it is distributed through fluid layers rather than concentrated at a ground boundary, so the vortex is not rapidly bled dry. The atmosphere provides depth, and depth allows the circulation to extend downward, storing momentum beyond the thin, visible skin. Jupiter's atmosphere is also thick enough to provide room for vertical structure, which can stabilize a vortex. A deep circulation can store momentum like a flywheel, harder to start but also harder to stop. If the red spot has a deep root, then its persistence becomes less mysterious and more inevitable. The red spot also sits in a field of strong jets that can confine it like rails. Adjacent east, west flows act like moving walls, shaping the vortex and limiting how it drifts, even as their shear threatens to tear it. The confinement is a kind of imprisonment, stability purchased by living inside a violent neighbourhood. That surrounding shear can feed it energy, even as it erodes the edges into filaments that peel away. The red spot's boundary often looks ragged in close views, as if the atmosphere is constantly trying to unspool it. The tension between feeding and shredding is visible, and that visibility makes the physics feel immediate. Its longevity likely comes from multiple supports working together, rather than a single simple cause. Internal heat drives turbulence that can merge smaller vortices into larger ones, and the vortex can absorb nearby storms. In fluid dynamics, merging is a pathway to longevity. Small swirls combine into fewer, larger structures that resist dissipation. When it absorbs them, it steals their vorticity and energy, growing stronger or at least renewing itself. The deep atmosphere may also provide a long-lived structure that anchors the circulation below the visible clouds, giving it a spine. The word spine is metaphorical, yet the idea is physical. Depth can hold a pattern in place. There is a quiet horror in that idea because it suggests memory in the flow. The vortex is not just spinning air at the top. There may be a deeper column that keeps the pattern coherent across years and decades. If a storm can remember, then the planet's atmosphere becomes less like weather and more like a living system. Yet the Great Red Spot is not immortal, and the evidence is now part of the story. Observations show it has been shrinking in size over decades, and careful tracking reveals changes in its shape, colour, and internal circulation. The change is slow, but it is persistent, which invites a question that has no easy answer. What does a centuries-old storm look like when it starts to fail? Modern imaging makes that change undeniable, because it turns sketches into measurements. The spot's long axis has shortened, its outline has become more compact, and the surrounding turbulence has grown more intricate. The camera can compare decades in seconds, and the time-lapse feels like watching a continent erode. Its colour and intensity vary, and its internal structure changes, with filaments and rings that appear and reorganise. Sometimes it deepens in hue, and sometimes it pales, as if the chemistry of its upper haze is being rewritten. That variability hints that dynamics and chemistry are coupled. Changes in circulation can change what sunlight can manufacture. Shrinking does not mean weakening in a simple way, which is one of Jupiter's subtler lessons. A smaller vortex can still have intense winds, because what changes is the balance between energy input and turbulent erosion. The storm may be tightening like a spinning skater, trading size for speed, even as it loses material at the edges. Interactions with surrounding jets matter as well, because the jets can both confine and distort the vortex. When the background flow shifts, the red spot can be stretched, squeezed, or made to shed material into the belts. The storm is not isolated. It is a feature embedded in a moving field, and the field can change. In high-resolution sequences, that shedding looks like smoke being pulled from a flame. Filaments peel away, wrap into the jet stream, and vanish into the banding, evidence that even a giant vortex is not sealed off from its environment. The planet is constantly recycling its own features, turning landmarks into raw material for new patterns. This is a key narrative beat, because it puts human time back into the frame. Jupiter can sustain a storm for centuries, then visibly reshape it within a human lifetime, reminding us that stability and change can coexist. The red spot becomes a clock not by ticking but by slowly altering its own face. The planet's atmosphere is stable in its violence, but not fixed in its details, and that distinction is unsettling. It suggests a system that will keep generating extremes, even as the specific shapes drift and evolve. The dread is not that Jupiter will calm down, but that it never needs to. The red spot's dread comes from scale and persistence, and from the way it makes size feel irrelevant. It has been larger than Earth in diameter at times in history, and it is still enormous today. When we compare it to our planet, the comparison feels unfair, yet the physics does not care about fairness. It is a reminder that Jupiter's weather is not a passing event, but a long-term state maintained by planetary physics. When we watch it spin, we are watching a reservoir of motion that does not quickly drain away. The storm is a visible ledger of energy, written in rotating cloud walls, Around it, smaller ovals and storms form, merge and vanish, like cells in a living tissue. Some are white ammonia storms with bright tops, some are darker features that hint at deeper layers, and some are transient outbreaks. The camera can drift across them and make the planet feel crowded, as if there is no empty sky anywhere. Those outbreaks can disturb whole latitude bands, changing their colour and texture for months or years. The atmosphere is crowded with rotating systems, because rotation and convection constantly generate vorticity and then sort it into coherent shapes. That sorting is a kind of self-organisation, and it raises an uncomfortable thought. How much order can emerge from pure physics? The sorting is part of the mystery, because it turns chaos into pattern without any guiding hand. Why do some vortices collapse quickly, while others lock into place and endure, as if the planet has chosen to keep them? The question is rhetorical, yet it points to real research, how turbulence, rotation, and stratification conspire to create persistence. At the poles, Jupiter shows another face of organisation, and it is as eerie as it is beautiful. Cyclones cluster and persist in polygon-like arrangements, suggesting stable patterns in a rotating fluid where symmetry can emerge from chaos. The details belong to later chapters, but the implication matters here. Jupiter can build architecture out of storms. Now we descend conceptually because Jupiter's vertical dimension is part of the fear. On Earth, altitude changes pressure slowly, and you can stand on something, even if the air above you is violent. On Jupiter, the absence of ground changes the meaning of safety, because there is no final boundary where the atmosphere must stop. On Jupiter, falling means entering thicker gas with no surface to catch you, and the word down becomes a one-way direction. The clouds are not a ceiling above ground, they are a layer within a deepening ocean of atmosphere. The view from above is deceptive. What looks like a surface is only a visible threshold. A probe that enters Jupiter meets increasing pressure almost immediately, and the change is relentless. The thin upper atmosphere gives way to denser layers, and the density rise changes everything about motion, heating, and structural stress. Even the sound of descent would change, because denser gas carries waves differently, though the probe would not survive long enough to listen. The entry itself is a violent negotiation with physics, because speed through gas turns into heat. A protective shield must absorb and shed energy, while the surrounding air compresses and glows, briefly turning descent into a kind of artificial meteor. The shock layer becomes a luminous shell, and the probe rides inside it like a spark inside a flame. Temperature rises with depth, and the chemical environment changes as compounds dissolve, react, and stop behaving like familiar clouds. What begins as ice crystals becomes droplets, then becomes fluid mixtures under conditions that blur everyday categories. The deeper you go, the less useful everyday words become, because the atmosphere refuses to stay in familiar states. At certain pressures and temperatures, substances can become supercritical, neither gas nor liquid in the normal sense. In plain terms, the atmosphere becomes a thick fluid, and the idea of a cloud as a floating layer starts to fail. The boundary between atmosphere and interior becomes a gradient, not a line, which is why the descent feels endless. The Galileo probe measured this descent in the 1990s, and it became a direct lesson in vertical extremes. Its instruments returned data as pressure climbed to many times Earth's sea level pressure, and as temperatures rose into punishing ranges. The probe's radio signal was a thin thread back to Earth, and the planet kept tightening its grip until the thread snapped. Galileo's descent also reminded scientists that local weather can fool a single measurement. The probe entered a relatively dry region, which meant fewer clouds than expected, and that surprise became part of Jupiter's lesson in variability. Even on a planet of global patterns, the local state can be harshly specific. One unlucky entry point can rewrite expectations. Those temperatures can destroy electronics and soften materials, even before the deepest regions are reached. The probe story is not just about numbers on a chart. It is about a machine being steadily overwhelmed by a planet's gradient. Each additional bar of pressure is not an abstract unit, but a multiplying load on seals, joints, and structure. Even before extreme depths, winds and turbulence create mechanical stress, and the stress is not gentle. A probe is buffeted by shear and updrafts, its parachute and structure tugged by competing flows, and its descent path bends sideways. The descent is not a straight fall, but a drift through currents, like a small boat in a stormy sea. The atmosphere is an ocean of gas, and the probe is a small object in a moving sea, with currents that do not respect a planned trajectory. Every kilometre downward is also a negotiation with the planet's horizontal power. The probe may be falling, yet the winds can carry it across longitudes, turning descent into a slanted, uncertain path. As pressure rises, the concept of flying changes in ways that are easy to underestimate. Lift and drag behave differently in dense gas. Forces on the structure increase, and heating from compression and friction becomes harder to manage. The same density that could help a parachute also amplifies the violence of gusts, making control a constant struggle. Eventually, the environment becomes crushing, and the word is not metaphorical. Pressure reaches tens of bars, then hundreds, then far more depending on how deep you imagine going, and each step multiplies the load on every surface. Even if materials could endure, the systems inside would face heat that accelerates every failure mode. Temperature climbs from cold cloud tops to hot, dense layers, where molecules move violently and electronics fail quickly. Even if a vehicle could withstand the pressure, it would face thermal conditions that erase margins and shorten lifetimes. The planet's gradient is not a challenge to be solved once, but a continuous escalation that never offers a plateau. The dread is not only heat and pressure, but the absence of a stopping point, which is psychologically different. Jupiter does not offer a surface where you can land, repair, or anchor, so descent is not a journey to a destination. It is a one-way surrender to deeper states, with no moment where you can say you have arrived. The deeper you go, the less the word surface means, because the planet is not built like a terrestrial world. What you call atmosphere gradually becomes interior, and the transition is smooth enough to deny you a moment of arrival. That smoothness is unsettling. Humans like boundaries, and Jupiter refuses to provide one. At some depth, hydrogen becomes a dense fluid, and the atmosphere transitions into the planet's interior. The boundary is gradual, not a cliff, and a descending probe would pass from gas to supercritical fluid without a clear threshold. The chemistry and physics continue to evolve, and the environment becomes less like weather and more like planetary matter. This is why landing on Jupiter is a category error, and the phrase itself becomes misleading. There is nowhere to stand, only deeper layers with higher pressure and higher temperature, and matter that behaves unlike familiar air. The planet offers no shoreline, only a deeper ocean, and the ocean grows stranger as you sink. The planet is a continuous gradient from cloud tops to exotic interior states, and that continuity is part of its menace. It is a world that does not grant the relief of a floor, only the certainty of increasing extremes. The visual beauty at the top is therefore a trap, because it hides how quickly conditions become unlivable. Winds make that impossibility practical, not just philosophical, because they turn the atmosphere into moving terrain. Jet speeds can reach hundreds of meters per second, and the shear between bands can be extreme, especially near jet boundaries. In those boundaries, the atmosphere can feel layered. Fast flow above, fast flow below, and a tearing zone between. In those boundaries, the air can feel like layered currents moving in opposite directions, separated by only a short distance. A vehicle crossing that line would experience sudden lateral forces, like crossing from one river into another. The force is invisible, yet the result is physical, and it would show up as stress, spin, and loss of control. Turbulence can twist, tumble, and stress any vehicle, while also complicating communications and navigation. A signal must fight not only distance, but the changing orientation of an object that is being shoved and spun by invisible currents. Even a stable antenna becomes a problem when the platform cannot hold still. If you tried to hover, you would need constant power to fight a moving fluid that never holds still. If you tried to descend slowly, you would still be carried sideways by jets and eddies, and your path would become a drifting arc. The planet would decide your trajectory, because its atmosphere is the dominant mass in the interaction. The atmosphere does not provide stable air, because stability is not its default state. It provides competing flows that never settle, and the competition is fueled by heat that keeps rising from below. The engine is always on, and the only question is how the energy chooses to express itself today. Even the idea of a calm layer is unreliable, because convection connects depths in a coupled system. Updrafts can punch upward, downdrafts can drag material down, and what seems quiet at one altitude can be disturbed by activity below. Jupiter's atmosphere is not a set of independent floors, but a connected column that transmits disturbance. This chapter's core claim is now clear, and it is meant to linger as an image. Jupiter's clouds are the visible output of an internal heat engine, organized by rotation into jets and expressed as storms that can outlast civilizations. The planet's beauty is therefore diagnostic. Every elegant stripe is a measurement of power. The Great Red Spot is the signature, but it is not the only proof, and the evidence is layered. Lightning shows deep water storms, microwave probing shows depth and structure, and bands and jets show a rotating fluid system redistributing heat. Each line of evidence is incomplete alone, yet together they form a coherent portrait of a deep, active world. The central question returns with sharper edges, because the facts point to an uncomfortable conclusion. What makes Jupiter terrifying is not only that it is large, but that its power is sustained, system-wide and indifferent to human timescales. If the engine has run for billions of years, what does it mean to approach it with machines built to last months? A world that radiates more heat than it receives is a world that never truly rests, even when sunlight is weak. A world with no surface is a world where descent is a one-way trip into pressure and heat. A world with many jets is a world where weather becomes architecture and architecture becomes motion. When you watch the stripes and vortices, you're watching a machine that has been running for billions of years. The motion is not decorative, it is the visible bookkeeping of energy, continually transported and continually rearranged. The question is not whether Jupiter will change, but how it chooses to change while remaining itself. Now we pivot from the visible to the hidden, because the storms are only the surface expression. Beneath the clouds, Jupiter's true power source sits deeper, where pressure rewrites matter into unfamiliar forms. The next descent is not through weather, but through physics, into states of hydrogen and helium that do not exist naturally on Earth. We leave the Great Red Spot behind as a warning sign, not a conclusion, because it is a symptom rather than the cause. The next chapter follows the energy downward, into the interior that feeds the storms and shapes the entire Jovian system. Jupiter's clouds look like a surface, but they are only a threshold, a bright skin of colour floating over a depth with no floor. Below them, there is no ground, only a continuous gradient of pressure and temperature that tightens like a slow, invisible vice. From far away, the bands seem painted on a sphere, yet up close they are weather, layered, moving, and endlessly falling into thicker air. The light we see is sunlight scattered by haze and cloud crystals, and that light fades quickly as you descend. Within minutes, the world becomes a dim amber tunnel, because the atmosphere itself becomes the medium that blocks vision. On Earth, you can fall until rock stops you, and even the deepest ocean gives you a bottom eventually. On Jupiter, down is a direction through states of matter, and the planet never offers a place to stand. There is no moment where you can say, here is the surface, because the boundary is not a boundary at all. Instead, Jupiter is a continuum, gas to fluid to something stranger, without a clean seam between one regime and the next. That is the first unsettling idea. The planet is not built like a world, but like an atmosphere that forgot to end. We use one brief descent as our anchor, because it actually happened, and because it left a trail of hard numbers. In 1995, the Galileo entry probe hit Jupiter's atmosphere at extreme speed, then began sending data as it sank. It was a small craft by planetary standards, roughly the size of a large barrel, yet it carried instruments designed to taste an alien sky. The mission itself had a long prelude, launched in 1989 and delayed by the slow geometry of interplanetary travel. By the time the probe separated from the Galileo orbiter, it was alone, aimed like a bullet at a target made of gas. The probe struck the upper atmosphere at roughly 47 kilometers per second, fast enough to cross a continent in a heartbeat. At that speed, the air in front of it could not move aside gently, so it compressed into a shock wave and heated violently. The probe's heat shield took the first punishment, because entry turns motion into fire and then into ionized plasma. For a short time, the probe was wrapped in a glowing sheath, and radio signals had to fight through that electrically charged veil. After the plasma glow faded, the real story began, because the environment kept tightening long after the flames were gone. A parachute deployed to slow the descent, and the probe began its careful work, measuring temperature, pressure, winds, and chemistry. In the visuals, imagine a small dark capsule hanging beneath a pale canopy, drifting through a sky that looks calm from orbit. Now imagine the calm dissolving into sheer, because Jupiter's atmosphere is stacked with jets moving at different speeds and directions. The probe entered a region later understood to be unusually dry, a so-called hotspot where clouds were thinner than expected. That surprise matters, because it reminds us how easy it is to mistake a single descent for the whole planet. Even so, the physics of pressure and heat are universal, and they are what ultimately ended the transmission. Pressure rose fast, measured in bars that climbed with every kilometre, and the climb was not linear. A bar is roughly Earth's sea level pressure, and Jupiter adds bars the way Earth adds meters in a deep lake. Temperature climbed with it, and the combination attacked electronics, seals and structure at once. As the air thickened, the probe's instruments faced a double assault: mechanical stress from compression and thermal stress from rising heat. Wires expand, solder softens, and tiny gaps that were harmless in space become leak paths under crushing force. The deeper it went, the more the probe was surrounded by a fluid that behaved less like air and more like a heavy, hot solvent. The probe did not reach the deep interior, yet its failure still teaches the rule, because Jupiter's gradient is the enemy. Jupiter's danger is not a single wall you cross, but an escalation that never stops. The last signals came from around 22 bars of pressure, where temperatures were already high enough to push hardware beyond its design. That number can sound modest, until you remember the probe was built for a brief, one-way plunge, not for survival. And it died early by Jupiter standards, because the planet's truly extreme pressures begin far below the level any probe has reached. So the Galileo descent becomes a parable. Even a carefully engineered visitor is only borrowing time. This is why the idea of landing is a category error, and the phrase itself misleads the imagination. Jupiter is built as layers that blend into one another, so the boundary between atmosphere and interior is not a line. If you tried to define a surface, you would have to choose an arbitrary pressure level, like choosing a shoreline in a fog bank. At the top, gases behave like gases, and clouds form where compounds condense out of the rising and falling air. Those clouds are not water clouds alone, but stacked chemistry. Ammonia ice higher up, ammonium hydrosulfide deeper, and water clouds lower still. Each cloud deck marks a temperature and pressure where a molecule changes phase, so the sky becomes a layered laboratory of condensation. In images, the bands and ovals are the visible tips of that laboratory, like foam patterns on a dark and restless sea. Deeper down, the same ingredients become dense fluids, and familiar phase boundaries start to blur. At a certain point, the distinction between gas and liquid becomes meaningless, because the fluid becomes supercritical. Supercritical means there is no sharp boiling or condensing, only a continuous change in density and behaviour as conditions shift. In plain terms, the atmosphere stops being air and becomes an ocean, yet it remains an ocean made of hydrogen. That ocean has no shoreline, no beach, and no stable platform, only pressure that increases as you sink. At still greater depths, hydrogen stops acting like the hydrogen we know, and this is where Jupiter becomes truly alien. Under crushing pressure, atoms are forced close enough that electrons move freely, and the material becomes metallic. Metallic does not mean it looks like a shiny ingot, because it is likely a hot, dense fluid rather than a rigid solid. Metallic means electrical conductivity, the ability to carry currents the way copper does in a wire. It also means new optical properties, so the interior would reflect and absorb light differently, if light could survive there at all. This transition is not just a curiosity, because it connects the planet's deep physics to the space environment far beyond the clouds. To make that scale intuitive, start with Earth's deepest ocean trenches, where pressure reaches about 1,000 bars. At those depths, the water is still liquid, yet the force is strong enough to crush unprotected steel and collapse empty cavities. Now compare Earth's mantle, where pressure rises to millions of bars and temperatures reach thousands of degrees. The mantle is solid rock, but it flows over geologic time, because heat and pressure make even stone behave like putty. Jupiter's deep interior pushes beyond those regimes in volume and in reach, because the planet is mostly the deep interior. On Earth, the extreme zone is a shell under our feet, but on Jupiter, the extreme zone is the planet's main body. The key point is not the exact number a probe would read at a given depth, because the numbers depend on models. The key point is that Jupiter's interior occupies pressure ranges where ordinary materials cannot keep their properties. Human engineering depends on stable solids, predictable seals, and electronics that stay cool enough to function. Jupiter's deep environment breaks those assumptions because heat and compression rewrite the rules of strength and stability. At high temperature, metals lose yield strength and begin to creep, which means they deform slowly under constant stress. At high pressure, any tiny flaw becomes a failure point because the force finds weaknesses and amplifies them. Even ceramics and exotic alloys face limits because the environment is not just strong, it is persistent and everywhere. Even if you could build a shell strong enough to resist collapse, heat would still win over time. Thermal energy drives diffusion, so atoms migrate and structures change, and what was hard becomes soft and what was sealed begins to leak. Metals creep, polymers fail, lubricants vanish, and circuits drift until they stop behaving like circuits. A battery's chemistry shifts, a sensor's calibration slides, and a transmitter's timing becomes noise in a rising thermal storm. In a visual sequence, the probe's clean geometry would seem to blur, as if the planet was slowly unmaking it molecule by molecule. That is the deeper terror. Not impact, not explosion, but relentless transformation under conditions that do not care. The deeper you go, the less useful the word atmosphere becomes because the concept is tied to thinness and breathing. The gas thickens into a supercritical fluid, and the planet becomes an ocean of hydrogen with no shoreline. In that ocean, buoyancy behaves differently, because density changes rapidly with depth, and composition can vary in subtle gradients. Hydrogen and helium dominate, yet trace compounds and heavier elements can alter opacity, conductivity, and how heat moves upward. You're no longer falling through air, you're sinking through a hot, compressible sea that is also the planet itself. That ocean is not passive, because Jupiter is still releasing internal energy that never fully dissipated. Convection moves heat upward, and the same deep engine that drives storms is rooted in this interior. Convection is simple in principle. Warm material rises, cool material sinks, yet on a rotating planet it becomes organized and fierce. Rotation twists rising plumes into columns and sheets, and it can lock motion into bands that persist for decades. So when we look at Jupiter's stripes, we are seeing the surface expression of a deep thermal machine. The clouds are not decoration, they are a readout, like ripples that reveal currents in a river you cannot see. Metallic hydrogen is the chapter's turning point, because it connects interior physics to system-wide consequences. If hydrogen becomes metallic, it can conduct electricity like a liquid metal, and that changes everything that follows. In laboratories on Earth, scientists have chased this state for decades, compressing hydrogen with diamond anvil cells and shock waves. Those experiments are difficult because hydrogen is the smallest atom, and it slips through materials and reacts in inconvenient ways. Even when metallic behavior is hinted at, it can be fleeting, because maintaining the required pressures is a technical cliff. Jupiter does not struggle to maintain those pressures because gravity supplies them continuously, and it supplies them at scale. Conducting fluid plus rapid rotation is the recipe for a dynamo, and Jupiter has both in abundance. Jupiter spins in about 10 hours, and that spin drives moving currents through the metallic layer. In a rotating conductor, the Coriolis force organizes flow, and organized flow can sustain magnetic fields against decay. A magnetic field wants to diffuse away, because electrical resistance turns currents into heat over time. A dynamo fights that diffusion by continually regenerating currents, using motion as the fuel and conductivity as the pathway. So the interior's metallic hydrogen is not just a strange phase, it is the wiring of a planetary generator. Those currents generate a magnetic field that is not a surface feature, but an interior product that fills space. The magnetosphere and radiation belts introduced earlier begin here, deep below the clouds in a region no camera can see. Field lines arc outward, trapping charged particles and guiding them into spirals that circle the planet at near-light speeds. In visuals, the field would appear as luminous loops, and the trapped particles would look like a storm of sparks in invisible cages. The auroras at Jupiter's poles are the visible signatures, where particles crash into the upper atmosphere and make it glow. So a deep physical transition, hydrogen turning metallic, becomes a light show at the edge of space. The dynamo is not a gentle generator, and the language of field can hide how violent it is. It is powered by planetary rotation and deep convection, and it produces a magnetic empire that traps particles and reshapes space. Jupiter's magnetic field is far stronger than Earth's, and its magnetosphere is so large it can engulf the Sun itself in scale comparisons. When the solar wind hits it, the boundary flexes and breathes, like a living thing responding to pressure. Inside, particles are accelerated, and the result is radiation intense enough to damage spacecraft and sterilize unshielded life. The interior, in other words, exports danger outward, turning deep physics into a hazard that reaches the moons. Jupiter's field is also not perfectly centered or simple, and that complexity is a clue about motion below. Juno's measurements show complex structure and strong regional variations, which implies complicated flows in the conducting interior. Instead of a clean dipole like a bar magnet, Jupiter's field contains lopsided patches and unexpected intensity gradients. That suggests the dynamo may be shallow in places, or that jets and interior winds reach down into conducting regions. It also suggests that the interior is not a neat textbook sphere, but a system with symmetries that persist. So the magnetic field becomes a diagnostic tool, a way to infer hidden circulation by reading patterns in space. So the interior is not just a static stack of layers, and it is not a simple onion with clean shells. It is a moving, evolving system that couples deep matter to auroras, radiation, and the hazards near the moons. If the flow changes, the field changes, and if the field changes, the radiation environment changes with it. That coupling makes Jupiter feel less like a planet and more like a machine, with feedbacks connecting deep and distant regions. And it raises a question that lingers. How stable is this machine over millions of years? And what does it mean for its satellites? Metallic hydrogen also reframes Jupiter's identity, because composition and behavior begin to echo stellar physics. A world made mostly of hydrogen and helium, with a conducting interior and self-generated magnetism, starts to resemble a star in composition. In a star, hydrogen is also the main ingredient, but it's held at pressures and temperatures that allow nuclei to fuse. Jupiter shares the ingredients, and it shares some of the mechanisms, yet it lacks the final step that makes a star. That near match is why Jupiter can feel like a failed star, a body that almost crossed a cosmic threshold. Yet Jupiter is not a star, and the reason is mass, which is ultimately the currency of gravity. To ignite sustained hydrogen fusion, you need far more gravity than Jupiter can provide, so core temperatures never reach the required threshold. Fusion is not simply heat, it is probability, because protons repel each other and must be forced close enough to interact. In the Sun, immense pressure raises density and temperature until quantum tunneling makes fusion possible at a steady rate. In Jupiter, pressure is enormous by planetary standards, yet it is still far below what is needed for long-term hydrogen burning. So Jupiter glows in infrared from heat, not from nuclear fire, and that difference defines its category. There is a near-miss category that helps explain the boundary, and it sits between planets and stars. Objects about 13 Jupiter masses can burn deuterium briefly, and we call many of them brown dwarfs. Deuterium is a heavier form of hydrogen with a proton and a neutron, and it fuses more easily than ordinary hydrogen. Because the barrier is lower, a smaller object can reach the required conditions, but only if it is massive enough. Brown dwarfs are sometimes called failed stars, yet they are also overgrown planets, and the names reveal our uncertainty. They can shine with internal fusion for a time, then fade as their deuterium supply runs out and they cool. Deuterium fusion is easier than hydrogen fusion, because the reaction barrier is lower, and the required temperatures are less extreme. Jupiter is still too small even for that, which is why it remains a planet by nuclear definition. This definition can feel abstract, yet it matters, because it ties identity to an internal process rather than to appearance. Jupiter looks bright, it looks dominant, and it looks like it should be more than a planet, yet physics draws the line. And that line is not about dignity or size. It is about whether gravity can turn hydrogen into a sustained nuclear engine. Still, Jupiter behaves star-like in other ways, and those behaviors are measurable rather than poetic. It emits more energy than it receives from the Sun, and that excess heat is measurable in infrared. If you could see Jupiter with heat vision, the planet would appear as a warm globe, with patterns that echo its atmospheric bands. The poles and belts radiate differently because circulation moves heat, and because clouds change how efficiently energy escapes. This internal glow is a reminder that Jupiter is not merely reflecting sunlight, it is still cooling from its own birth. The simplest source is leftover formation heat, stored when the planet assembled from the solar nebula. When gas falls into a growing planet's gravity well, it accelerates, and that kinetic energy becomes heat when it is stopped. Early Jupiter was a place of shocks and impacts, wherein falling material delivered energy as surely as it delivered mass. The second source is slow contraction, the Kelvin-Helmholtz mechanism, turning gravitational energy into heat. As Jupiter contracts by a small amount, gravity does work on the interior, and that work becomes thermal energy. In plain terms, the planet is slowly settling, and the settling keeps it warm. That slow squeeze is tiny in radius but enormous in power, because Jupiter's mass is enormous and its interior is vast. Over billions of years, contraction becomes a steady furnace that never fully shuts off, even as the planet cools. The process is slow enough that Jupiter remains stable, yet persistent enough that it continues to influence weather today. This is one reason giant planets can stay active for so long after smaller worlds have lost their internal heat. It also means Jupiter is not a frozen relic, but an evolving body still spending the energy of its formation. Internal heat matters at the cloud tops, because it drives convection that feeds storms and maintains jet streams. The Great Red Spot and the banded jets are surface expressions of a deep thermal engine, not mere wind patterns. The red spot is a long-lived vortex, a storm larger than Earth, and its persistence hints at energy supplied from below. Even as it changes size and colour, it remains a symbol of longevity, as if Jupiter can sustain weather for centuries. The bands, meanwhile, are like conveyor belts of air, alternating east and west in a pattern shaped by rotation and heat. So when you watch the clouds race, you are watching heat escape from the deep interior in a form the eye can follow. So the terror is not only local, like winds that shred a probe or lightning that flashes in hidden depths. The terror is systemic because Jupiter's interior power shapes the entire environment around the planet. Internal heat strengthens convection, convection strengthens the dynamo, and the dynamo strengthens the radiation belts. The chain links deep physics to space hazards, and it does so with no single point you can isolate and avoid. In that sense, Jupiter is dangerous in the way a star is dangerous, because its energy and fields extend far beyond its visible edge. Now the chapter turns to what we do not know, because the core remains an open question even after decades of study. Jupiter almost certainly contains heavy elements, but we still debate how they are arranged and how sharply they are separated. The word core can mislead, because it suggests a solid ball like Earth's, yet Jupiter's centre may be more complex. At extreme pressures, rock and ice do not behave the way they do on Earth's surface, and mixtures can form exotic fluids. So when we talk about a core, we may be talking about composition more than state, an enrichment rather than a rigid object. One model imagines a compact core, a dense central region enriched in rock and ice, surrounded by hydrogen and helium. This picture aligns with classic formation ideas, where a solid seed grows first and then captures gas from the disk. Another model imagines a diluted core, where heavy elements are mixed outward into the metallic hydrogen. In that case, the centre is not a clean boundary, but a gradient, like ink diffusing into water under slow stirring. A diluted core could form if the early core was partly eroded by convection, or if impacts stirred heavy material upward. Both models can match parts of what we see, which is why the debate remains alive. Juno's gravity measurements add pressure to the debate, because gravity reveals how mass is distributed inside the planet. As Juno passes close to Jupiter, the planet's uneven gravity tugs on the spacecraft and changes its velocity by tiny amounts. Those changes are measured through radio tracking, where Doppler shifts reveal accelerations too small to feel but large enough to compute. From that data, scientists infer gravitational harmonics, a kind of fingerprint of interior density and flow. The method is indirect, yet powerful, because gravity cannot be hidden by clouds or darkness. Those constraints suggest Jupiter may not have a sharp boundary between core and envelope, at least not the kind we expected. The data can be read as evidence for a fuzzy, extended region of heavy element enrichment, spread across a large fraction of the radius. That interpretation implies mixing, and mixing implies motion, because diffusion alone would be too slow on planetary timescales. It also implies that Jupiter's interior may be layered in a more subtle way, with composition gradients that affect convection. A gradient can stabilize certain regions, slowing mixing, while other regions remain turbulent and efficient at transporting heat. So the core question becomes a circulation question, and the circulation question loops back to the dynamo. That fuzziness matters for formation history, because it hints at how Jupiter grew and how violent its early life may have been. A compact core supports classic core accretion, where a solid seed forms first and then captures gas. In that scenario, the seed might be several Earth masses, built from rock and ice in the cold outer disk. Once it becomes massive enough, gas falls in rapidly, and the planet's growth accelerates like a runaway. That runaway phase would shape the disk, carving gaps and altering how material flows toward the Sun. So a compact core is not just an interior detail, it is a clue to how the entire system evolved. A diluted core can support scenarios where impacts, mixing and erosion redistributed heavy elements after formation. It can also hint at violent early events, including giant collisions that delivered energy and stirred the interior. A large impact could deposit heavy material, disrupt stratification, and change how heat escaped for millions of years afterward. Even without a single dramatic collision, steady accretion of planetesimals could rain heavy elements into the envelope over time. The planet would then be less like a neatly assembled object and more like a cauldron, continually stirred as it grew. The mystery is not whether Jupiter has heavy elements, but how the planet chose to store them. There is also disk instability, where parts of the gas disk collapse directly into a giant planet under their own gravity. That pathway can build a massive world quickly, but it must still explain Jupiter's composition and its enrichment in heavier elements. If Jupiter formed by rapid collapse, it might begin more uniform, then later acquire heavy elements through accretion and mixing. If it formed by core accretion, enrichment is built in from the start, yet later evolution could still blur boundaries. So the interior is a record of competing processes, and the record is written in densities we cannot touch. Composition is the fossil record, because Jupiter kept much of the primordial nebula that the rocky planets lost. The ratios of elements and isotopes tell us where it formed, what ices were available, and how the disk was structured. Helium abundance, noble gases, and isotopic signatures act like timestamps, because they reflect conditions in the early solar environment. Some measurements come from remote sensing, and some come from in situ data like Galileo's, yet each has uncertainties. Even the act of sampling is complicated, because Jupiter's atmosphere is dynamic and can hide deeper composition under weather layers. Still, the broad message is consistent. Jupiter is not pure hydrogen and helium, it is enriched by material that once froze. Jupiter's enrichment in certain elements suggests it accreted solids and ices along with gas, not gas alone. That points to a cold formation environment, beyond key snowlines where volatiles condense into grains and pebbles. Snowlines are distance markers in a disk where temperature drops enough for water, ammonia or carbon dioxide to freeze. Beyond those lines, solid material becomes more abundant, and building a massive core becomes easier. So Jupiter's chemistry implies a birthplace in a region where ice was common, and where the disk could feed rapid growth. In visuals, the young solar system becomes a dusty whirlpool, with invisible temperature rings shaping what can form where. But Jupiter is not guaranteed to have stayed where it formed, and the evidence for migration is written in the system's architecture. Migration is expected in young disks, and a moving Jupiter would have reshaped the entire early solar system. As a giant planet interacts with the gas disk, it can exchange angular momentum and drift inward or outward over time. That drift can be slow or rapid depending on disk conditions, and it can change the fates of smaller bodies dramatically. So Jupiter's present orbit may be the end of a journey, not the place where it began its influence. If Jupiter migrated inward and then outward, it could have scattered planetesimals, starved Mars, and rearranged the asteroid belt. It could also have delivered or removed water-rich material that later built Earth, depending on timing and pathways. The asteroid belt's mixed composition, with dry and water-bearing bodies, can be read as a signature of past stirring. In this view, Jupiter is not just a planet, it is a gravitational plough that moved through the disk and redistributed debris. The inner planets may owe their sizes and compositions to that redistribution, which makes Jupiter's origin a story about us. And it raises an uncomfortable thought. How many Earth-like worlds never form because a Jupiter-like giant takes a different path? So the interior is not only a curiosity about exotic hydrogen, and it is not only a physics lesson in extreme matter, it is the reason Jupiter became the system's architect. Because mass and formation history decide where gravity applies its long leverage. A planet's interior determines its radius, its density profile, and its ability to grow. and those traits determine its gravitational reach. The same deep mass that makes metallic hydrogen also makes Jupiter a sculptor, shaping orbits and clearing regions of space. So when we talk about the core, we're also talking about the early solar system's blueprint. This is where the existential tension sharpens, because small differences in mass and motion can rewrite a planetary system. A Jupiter-like world changes what a solar system can be, because it controls the distribution of material and the stability of orbits. It can protect inner planets by deflecting comets, or it can endanger them by sending debris inward, and the balance can shift. It can open gaps in disks, alter where planets form, and lock smaller worlds into resonances that persist for eons. So Jupiter's interior is not hidden trivia. It is the engine behind the planet's ability to influence everything else. A slightly bigger Jupiter could have become a brown dwarf, changing the Sun's neighborhood into a binary-like system. That would change illumination, radiation environments, and the gravitational choreography of the planets. A slightly different migration could have prevented Earth from assembling at all, or could have left it dry and barren. These are not fantasy alternatives, because exoplanet surveys show many systems with hot Jupiters and disrupted architectures. Our system's relative calm may be a narrow outcome, and Jupiter's mass and history may be part of why it happened. So the question becomes personal. How much of our existence depends on a giant planet that never became a star? Jupiter's interior therefore becomes a story about thresholds, because thresholds are where nature changes behavior. Pressure turns hydrogen metallic, rotation turns that metal into magnetism, and mass almost turns a planet into a star. Each threshold is a phase change in the broad sense, a point where new rules dominate and new consequences emerge. The planet is a ladder of such changes, and descending it is like moving through different universes of physics. Even our language strains because words like gas and ocean and metal begin to overlap in ways they never do on Earth. So Jupiter becomes a reminder that the categories we live by are local conveniences, not universal truths. The chapter returns to the central question with a deeper answer, because the terror is not only in what we see. Jupiter is terrifying because its power is not only atmospheric or magnetic, but structural, built into how the planet exists. It is a world where pressure is destiny, where heat is persistent, and where the absence of a surface is not a detail. From Earth, Jupiter looks like a calm bead of a light, bright enough to guide ancient navigators across dark skies. Up close, it is a failed star with planetary consequences, still glowing, still generating magnetism, still rewriting its surroundings. In the final visuals of this chapter, the camera pulls back from the clouds into darkness, and the magnetic field lines remain. They remain because they are anchored in the deep, in metallic hydrogen, in the slow furnace of contraction. We have now seen what Jupiter is, beneath the clouds and beneath the names. Next, we track what Jupiter does, because gravity turns this interior mass into a sculptor and an executioner. We leave the deep interior with one conclusion that will drive the next chapter. Jupiter's greatest weapon is not a storm or a belt of radiation, but the long reach of its gravity. Jupiter's storms and radiation feel immediate, but gravity is the deeper threat because it acts even when nothing seems to happen. Gravity reaches across the solar system, tugging quietly for millions of years, and its patience is what makes it dangerous. After the Sun, Jupiter dominates the system's choreography through mass alone, carrying more than twice the mass of all other planets combined. From a distance, it looks like a steady lantern, yet its influence is written into the timing of the worlds. Gravity is not a push, it is a long-range pull that never turns off, and it does not need contact to change a destiny. In modern terms, gravity reshapes trajectories by exchanging energy and angular momentum, even when the exchange is tiny. A small pull, repeated constantly, can change an orbit completely, the way a slow leak can empty a tank. That is perturbation in plain language. Jupiter keeps nudging, and the nudge accumulates until the old path is no longer the easiest path. In space, most objects follow stable paths until something changes their timing, because timing controls where bodies meet and how close they pass. Jupiter changes timing by changing speed, direction, and distance at each pass, and those changes alter the next pass as well. Over many orbits, those tiny changes become new routes, new collisions, and new impacts, even though no single moment looks dramatic. If you could watch the solar system in fast motion, you would see orbits breathe and precess, slowly twisting like threads under tension. Resonance is the amplifier that makes the nudges matter because it turns random taps into a repeating beat. If two bodies repeat a pattern, the tugs line up like repeated pushes on a swing, arriving at the moment that adds energy instead of cancelling it. Mean motion resonance means a simple ratio of orbital periods, and the ratio locks the timing so the geometry repeats. A 3.1 resonance, for example, means an asteroid completes 3 orbits for every one of Jupiter's, meeting Jupiter's influence at the same rhythm. When the timing locks, the force does not need to be large because repetition is a kind of power. The same gravitational beat hits again and again at the same orbital phase, and the orbit responds like a system being driven at its natural frequency. The orbit can stretch, tilt, or become chaotic without any single dramatic encounter, because the change is distributed across thousands of returns. What looks like empty space becomes a metronome, and Jupiter is the hand that keeps time. This is why Jupiter is terrifying as an architect. It can sculpt the solar system without touching anything directly, shaping gaps, clusters, and escape routes with invisible geometry. It can also become an executioner, because the sculpture can aim debris inward, turning distant leftovers into near-term hazards. The chilling part is the delay. Effects can be set in motion now and arrive long after the cause is forgotten. The asteroid belt is the clearest place to see this architecture, because it sits in the middle distance where Jupiter's pull is strong and persistent. Between Mars and Jupiter, countless bodies orbit in a broad ring of leftover material, a population that never became a planet. Through a telescope, the belt is mostly absence, but in data it becomes a swarm of numbered worlds. The belt looks like a reservoir, but Jupiter turns it into a machine, sorting by resonance the way a prism sorts light. Kirkwood gaps are the belt's missing lanes, and they are not random, even though they look like accidents at first glance. They mark locations where asteroids would orbit in resonance with Jupiter, such as the 3:1, 5:2, and 2:1 ratios. At those ratios, repeated tugs destabilize orbits until the lane empties, leaving a statistical scar in the distribution. When Daniel Kirkwood identified these gaps in the 19th century, he was seeing gravity's handwriting before computers could draw it. A gap is not empty because nothing formed there, because the early belt likely formed bodies across a wide range of distances. It is empty because resonance makes long-term survival unlikely, and survival is the true filter of the solar system. Jupiter clears by raising eccentricity, pushing orbits into crossings and collisions, and those collisions grind bodies down into fragments. An asteroid that once traced a neat circle becomes a needle that stitches through the belt, intersecting neighbours until something breaks. Resonances also concentrate objects into dangerous pathways, because not every resonance simply removes bodies from view. Some regions become source zones that feed near-Earth asteroids, acting like on-ramps to the inner system. Jupiter's gravity does not only remove bodies, it sorts them into outcomes, separating the stable from the doomed. The belt becomes less a ring and more a network, with junctions that lead outward, inward, or into destruction. One key pathway is the delivery of meteorites to Earth, a link that turns abstract dynamics into something you can hold. Many meteorites are fragments from the belt, liberated by collisions and then guided by dynamics that favour certain exits. Resonances can pump their eccentricity until they cross Mars, then Earth, and once a fragment becomes planet-crossing, it enters a different regime of repeated encounters. The next time a meteorite hisses through our atmosphere, it is finishing a journey that began with Jupiter's steady pull. The belt is also shaped by families, groups of fragments from ancient breakups that still share a genetic signature. A collision creates a cloud of debris with similar orbits at first, like shrapnel expanding from an explosion in slow motion. Over time, Jupiter's resonances then shear that cloud, spreading fragments into streams and escape hatches that intersect resonant boundaries. When astronomers map these families, they are reconstructing catastrophes that happened before complex life existed on Earth. Some families become long-lived, and some become pipelines, depending on where their fragments drift. A fragment can drift slowly through subtle forces, then hit a resonance boundary, and the drift can be driven by sunlight itself. The Yarkovsky effect, tiny thermal recoil from absorbed and re-emitted heat, can move small bodies over millions of years, centimetre by centimetre in orbital distance. Once it enters that resonance, Jupiter does the heavy lifting, converting a slow drift into a fast change in eccentricity. This is the first trade in Jupiter's story, because the same mechanism can reduce one risk while increasing another. Clearing lanes can reduce local density in some regions, lowering collision rates and stabilizing certain neighborhoods. But concentrating bodies into unstable routes can increase delivery to the inner planets, feeding a steady trickle of impactors. Jupiter is not a simple broom, because it also builds the chute. Comets raise the stakes because their energies are higher and their origins are farther, and their compositions carry volatile ices that respond dramatically to sunlight. Beyond the asteroid belt, icy bodies orbit in colder reservoirs, where water, carbon dioxide and carbon monoxide can remain frozen for eons. Jupiter sits near the gateway between those reservoirs and the inner system, close enough to redirect traffic but far enough to act as a filter. In wide-field images, comets appear as faint smudges, yet their orbits can carry the kinetic energy of global catastrophe. Jupiter family comets are defined by Jupiter's control over their periods and paths, a definition that is dynamical rather than poetic. They are short-period comets whose orbits have been reshaped by Jupiter encounters, often with periods under about 20 years. Many were once farther out, then were captured into tighter loops, and their repeated returns let us watch evolution in real time. Each pass near the Sun boils away surface layers, changing jets, spin, and sometimes the comet's survival. Capture is not a gentle adoption, it is a gravitational bargain that depends on geometry and timing. A close pass can steal energy from a comet's orbit relative to the Sun, because the comet trades energy with Jupiter's moving gravitational field. In the planet's frame, the encounter can look symmetric, yet in the Sun's frame, the comet can leave with a different speed. The comet's path shrinks, and it returns more often, now a recurring visitor that keeps crossing the inner system's lanes. The same process can also eject comets completely, which is why Jupiter's reputation as a shield is not entirely myth. A different geometry gives the comet extra energy instead of taking it away, and the comet can be accelerated beyond the Sun's escape speed. Jupiter can fling a body outward, turning a threat into an exile, and that exile can be permanent on human timescales. In simulations, many comets are removed this way, disappearing into interstellar darkness after one decisive encounter. That is why Jupiter can look like a shield, because it can intercept, capture, or eject bodies that might otherwise reach Earth. But the same interactions can inject new threats inward on fresh trajectories, and those trajectories can be steep, fast, and unfamiliar. The shield and the slingshot are the same tool, just used with different angles. If you stand on Earth and watch the sky, you cannot tell which role Jupiter played in the background. A comet that would never cross Earth can be redirected into the inner system, because Jupiter can rotate the orbit's line of apsides and change where the closest approach occurs. A single Jupiter encounter can lower perihelion and change inclination, and those changes can move a comet into the plane where planets live. The result can be a new impactor class with little warning, because long-period visitors can appear from the outer dark with high speed. The most unsettling threats are not the ones we track for decades, but the ones that arrive on a first visit. The outer system also contains long-period comets, arriving from distant reservoirs that may extend tens of thousands of astronomical units. Jupiter can deflect them, but it can also break them, because gravity is not only a steering force but a stretching force. Tidal forces during close passes can fragment a nucleus into multiple projectiles, especially if the nucleus is already a weak rubble pile. In that moment, a single orbit becomes a branching family tree, each branch carrying its own impact probability. Fragmentation changes the risk profile in a way humans understand, because it turns one concentrated disaster into a distributed sequence. One large impact becomes many smaller impacts over days or weeks, and the timing can be determined by how the fragments spread along the orbit. The energy is redistributed, but the spectacle becomes a chain of strikes, and the psychological effect is its own kind of damage. On Jupiter, such chains can be watched from afar, giving us a rare laboratory for what tides can do. Shoemaker, Levy 9, is the modern demonstration that ends any illusion of gentleness, and it arrived like a message written in fire. The comet was captured, then torn into fragments by Jupiter's tides, likely during a close pass that pulled it past its structural limit. In 1994, those fragments hit Jupiter in a visible sequence, each impact timed like a grim schedule. Astronomers around the world coordinated observations, because the solar system was about to show its mechanics on a planetary screen. The impacts were not subtle, and the visuals still feel unreal even in archival footage. They produced fireballs, plumes, and dark scars larger than Earth, with ejecta rising thousands of kilometers above the cloud tops. For a moment, Jupiter became a screen that displayed gravitational violence in real time, and the scars rotated into view like bruises on a giant. Infrared images revealed hotspots that lingered, because the impacts punched energy deep into the atmosphere. Shoemaker, Levy 9, is not only a historical event, it is a rehearsal, because it demonstrates a full chain of capture, fragmentation, and collision. It shows that Jupiter can turn a comet into a train of impactors, and that the train can stay coherent long enough to strike repeatedly. It also shows that a giant planet can absorb blows that would sterilize a smaller world, because its atmosphere and gravity can dissipate energy without exposing a solid surface. Watching Jupiter take the hits forces a question. How many times has Earth been spared, and at what cost elsewhere? The scars faded, but the lesson stayed, because fading is not forgetting in celestial mechanics. Jupiter's gravity can rearrange bodies, and Jupiter's size can take the hit, absorbing impacts that would rewrite Earth's biosphere. The question is whether that protects Earth, or merely changes which threats reach us, because removal and redirection are different outcomes. In the long view, protection is not a feeling, it is a statistical shift. Impact history on Earth carries the same ambiguity, and the rocks keep the record even when memory does not. Large impacts have shaped climate, biology, and extinction, injecting dust and aerosols that can cool the planet and collapse food chains. The cratering record and the fossil record both testify to periodic catastrophe, even though erosion and plate tectonics erase many older scars. When geologists find shocked quartz or iridium anomalies, they are reading signatures of violence from space. Some of those impactors likely came through Jupiter-influenced pathways, because the belt and the comet reservoirs are coupled to Jupiter's resonance structure. Resonances deliver asteroids, and Jupiter encounters redirect comets, and both processes can raise the rate of Earth crosses over long intervals. Even when the final strike is local, the upstream dynamics can be Jovian, operating far beyond the orbit of Mars. The unsettling idea is that Earth's most intimate disasters can have remote causes. Yet Earth is still here, and that fact tempts a simple story because survival invites a narrative of guardianship. It is easy to call Jupiter a guardian that sweeps the sky, removing would-be killers before they reach us. It is also easy to call Jupiter a villain that loads the gun, feeding impactors into the inner system with resonant precision. The truth is harder, because the solar system does not care which story we prefer. The shield versus threat debate is not settled, because the system is non-linear, meaning small changes can produce disproportionate outcomes. Simulations show outcomes depend on Jupiter's mass, orbit, and eccentricity, and they depend on the initial distribution of small bodies as well. Change the parameters, and the impact rate can go up or down, sometimes in counterintuitive ways. In some scenarios, Jupiter reduces long-period comet impacts, but increases certain asteroid deliveries, and the balance becomes a moving target. A more massive Jupiter can eject more comets, which sounds protective, because ejection removes potential impactors from the system entirely. But it can also perturb more strongly, which can inject more bodies inward, particularly from resonant regions that become more efficient at pumping eccentricity. The same strength that clears can also aim, and aiming is what turns distant debris into a near-Earth problem. In a gravitational system, power is never single-purpose. A less massive Jupiter can fail to eject, leaving more threats in the system, and those threats can linger for millions of years. But it can also perturb less, reducing injection into Earth-crossing orbits, and that reduction can matter if the main hazard is delivery rather than retention. The safest Jupiter might not be the biggest Jupiter, because safety depends on which pipeline dominates. The uncomfortable implication is that habitability may hinge on fine details of giant planet architecture. Orbital shape matters as much as mass, because eccentricity changes how widely a planet sweeps through space. A more eccentric Jupiter sweeps a wider range of distances each orbit, and that wider sweep can destabilize more regions and broaden resonance effects. The resonant locations shift slightly, and the strength of perturbations changes with distance, altering which parts of the belt become leaky. Even a modest eccentricity can translate into a large change in long-term delivery rates. Inclination matters too, because it changes which populations are strongly coupled and which are relatively insulated. A slightly tilted orbit can stir different reservoirs, reaching into populations that would otherwise remain quiet. The architecture of risk depends on geometry, not morality, because gravity responds to configuration rather than intent. If you could tilt the entire system by a few degrees, you would rewrite the map of resonant highways. So Jupiter is not purely protector or destroyer, and the language of character is only a metaphor for statistics. It is a gravitational engine with outputs that depend on initial conditions, and those conditions were set during formation. The terror is that the same planet can play both roles without changing its nature, because the role is assigned by context. A stable-looking orbit can still be a catalyst, because stability for one body can mean instability for another. To understand why, we have to return to the early solar system, when orbits were not settled and the disk itself was evolving. The planets formed in a disk of gas and solids, and the disk was moving, turbulent, and structured by pressure gradients. In that era, Jupiter's gravity did not just sculpt debris, it moved the boundaries of where planets could exist. Because giant planets interact strongly with gas, the young sun was surrounded by a luminous, dusty plain, and within it the future was negotiable. Planetary migration is the mechanism that makes early history feel dangerous, because it means planets did not necessarily form where we find them today. Young giant planets exchange angular momentum with the gas disk, and that exchange can move a planet inward or outward over time. In simple terms, the disk pushes back, and the planet responds, drifting through regions filled with planetesimals. Migration turns a planet into a moving resonance source, sweeping gravitational patterns across the system like a comb. The Grand Tack is a simple story with brutal consequences, and its name evokes a sailboat changing direction against the wind. Jupiter may have migrated inward toward the region of Mars, then reversed direction, and the reversal is the key drama. Saturn's growth and resonance with Jupiter could have pulled Jupiter back outward, locking the two giants into a coupled migration. If that happened, the inner system would have been compressed and then released, and the debris would have been scattered in both phases. If Jupiter moved inward, it would have disrupted the material that might have built a larger Mars, because it would have truncated the inner disk of solids. It could have truncated the inner disk, starving Mars of building blocks, and leaving Earth and Venus with more of the remaining mass. That offers a pathway to explain why Mars is small, a planet that looks like it stopped growing mid-sentence. The idea is not that Mars failed on its own, but that Jupiter edited the script. The same migration could have mixed the asteroid belt, and the belt's odd diversity makes that mixing feel plausible. It could have scattered inner dry bodies outward, and outer icy bodies inward, blending compositions that should not sit side by side. The belt's mixed composition becomes a fossil of that stirring, with some asteroids resembling baked rock and others carrying more primitive carbon-rich material. When spacecraft visit these bodies, they are sampling a shuffled deck left behind by migration. Migration also affects water delivery, which ties Jupiter directly to habitability, because water is both a solvent for chemistry and a regulator of climate. Water-bearing bodies from beyond the snowline can be redirected inward, and the snowline itself moved as the young sun brightened. Jupiter can either block them, deliver them, or scatter them into new reservoirs, depending on where resonances sweep and where encounters occur. If Earth's oceans were partly delivered by such bodies, then Jupiter's early motion helped decide how wet our world would become. The Nice model extends this idea into a later reshuffling, after the gas disk dissipated and the giants interacted mainly with leftover planetesimals. The giant planets may have shifted positions after the gas disk dissipated, trading angular momentum with a massive outer disk of small bodies. Resonance crossings could have destabilized small body reservoirs and triggered bombardment, sending waves of objects inward. In that picture, the solar system's calm was not original, it was achieved after episodes of rearrangement. In that picture, Jupiter is a trigger as well as a sculptor, because triggers can be small and still be decisive. A small change in giant planet spacing can cascade into system-wide chaos, and the cascade can last long enough to matter for emerging life. The inner planets feel the consequences as impacts and orbital stirring, and the difference between a gentle epoch and a violent one can be a resonance crossing. The frightening part is how little needs to change to start the chain. These models are debated in details, but their shared message is clear, and it changes how we interpret the present. Jupiter's present orbit may be the endpoint of migration, not the starting point of formation, and endpoints hide the path taken. The early path matters because it sets the starting conditions for everything that follows, including which reservoirs exist to feed later impacts. When we look at today's stable planets, we may be looking at survivors of an earlier instability. Jupiter's gravity also preserves fossils of that early era in stable traps, places where objects can linger for billions of years. The Trojan swarms at L4 and L5 orbit with Jupiter, 60 degrees ahead and behind, like two flocks keeping formation. They are not random asteroids. They are captured populations in gravitational balance, held in place by the combined geometry of Jupiter and the Sun. In wide shots, you can imagine them as faint clouds embedded in Jupiter's orbit, almost invisible until you know where to look. L4 and L5 are stable because forces and motion create a restoring geometry, and the stability is subtle rather than absolute. A body that drifts is nudged back into the region over time because the gravitational pulls and the orbital motion create a kind of valley in the effective potential. The result is a long-lived cloud of objects sharing Jupiter's orbit, librating around the Lagrange points rather than sitting still. Stability here is dynamic, a constant correction rather than a fixed anchor. Trojans matter because they are time capsules, and time capsules are rare in a system that constantly collides and erodes. Their compositions and size distributions can preserve information about where they formed, because they may have avoided the intense collisional grinding of the main belt. Some may have originated far from Jupiter, then were captured during migration, and that capture would have frozen a snapshot of early mixing. When we measure their spectra, we are testing a hypothesis about the solar system's youth. Studying them tests formation and migration models, because different histories predict different Trojan origins and compositions. If Trojans resemble outer solar system bodies, that supports large-scale mixing and capture from distant reservoirs. If they resemble local material, that supports a quieter history with more in-place formation. Either way, the Trojans are evidence that gravity can store memory, and that memory can be read with modern instruments. Captured populations also reveal Jupiter's role as a collector, because capture is another form of sculpting. Jupiter can trap objects temporarily, then release them later, and temporary capture can last months, years, or longer. Temporary capture can turn a distant body into a short-term resident, then into an inner system threat, because the release can occur onto a new orbit. The solar system has a hidden category of objects that are not permanent members of any region, only travelers passing through Jupiter's jurisdiction. Even Jupiter's moons carry the imprint of this gravitational regime, because resonances do not stop at the edge of the planet's Hill sphere. Their resonances drive tides, heat, and volcanism, especially at Io, where orbital forcing kneads the interior like dough. The same gravitational logic that shapes asteroids also powers geological violence, turning orbital energy into heat through friction. When we see Io's lava fountains or Europa's fractured ice, we are seeing resonance made visible. So the chapter's climax is not a single impact, but a system-wide pattern that repeats across scales. Jupiter's gravity is a lever that moves debris, planets, and water, and the lever works whether we watch it or not. It can reduce risk by ejecting threats, and increase risk by feeding impact pathways, and the balance can shift over time. The solar system is not a static arrangement of spheres, but a living dynamical system with long memories. The central question sharpens here, because the answer is not a simple label, and labels can be comforting in a way nature is not. Jupiter is terrifying because its influence is indirect and delayed consequences are the hardest to intuit. It can set up consequences that arrive millions of years later, on worlds that never interacted with it directly, because resonances propagate influence through chains of orbits. In that sense, Jupiter's gravity is a kind of distant governance, indifferent to who is affected. From Earth, Jupiter still looks like a calm bead of light, steady in the night and familiar to every generation. That calm is the mask of a gravitational machine that never sleeps, because the equations do not pause. The planet's beauty hides a long-range weapon that can rewrite the odds of survival, shifting probabilities rather than issuing certainties. When you look at Jupiter through a backyard telescope, you're seeing a serene face attached to an enormous dynamical reach. We end with the present tense because the architecture is still active and the machine is still running. Resonances still pump eccentricities, and comets still pass through Jupiter's gate, and the belt still leaks fragments into the inner system. Every mission that approaches Jupiter enters a region shaped by this deep, indifferent power, where navigation must account for both gravity and radiation. In the background, the same forces that steer spacecraft also steer natural bodies, and the difference is only intent. After seeing Jupiter's system-wide influence, we return to the present. To learn the truth, spacecraft must survive Jupiter's hazards long enough to measure them. because measurement is our only way to turn awe into understanding. The final chapter asks what we can know and what Jupiter still keeps hidden behind clouds, magnetic fields, and the quiet persistence of gravity. Every Jupiter mission is a countdown because dose budgets make time literal. In the belts, energetic electrons and ions slam into metal and silicon, slowly flipping bits and cracking materials at the atomic scale. Engineers hide computers in radiation vaults, stack shielding like armor, harden chips, add redundancy, and plan trajectories that minimize belt exposure. Polar orbits dive and retreat, skimming the worst zones instead of lingering in them, while instruments duty cycle to reduce risk. Failures are assumed and contained because a single upset can cascade into silence. This is the climax of survival, because Jupiter punishes every shortcut. On the approach, the planet swells from a star to a striped world, and the auroras flare like curtains pinned to invisible field lines. Even the camera becomes a witness to hazard, grainy noise, sudden glitches, and the constant threat of a permanent blackout. Yet, the payoff is fundamental. Juno mapped magnetosphere currents, auroral engines, and wave acceleration that feeds the kill zone belts, showing how energy moves from rotation into particles. Those measurements turn the aurora into a diagnostic, not just a spectacle, revealing where plasma is heated and where it escapes. Microwaves and gravity tracking constrained atmospheric depth, jet routes, and a diluted core that rewrites formation models. The numbers hint at heavy elements stirred upward, and at a past collision that may have blurred the boundary between core and envelope. Those measurements connect back to the origin story. Since the first telescopic sketches, Jupiter has been our benchmark for giant planets, and now it anchors models built for distant systems. Gas giants are common around other stars, and Jupiter becomes our calibration target for exoplanet spectra, migration histories, and system architecture. When we interpret a faint transit signal, we're quietly asking how Jupiter formed, moved, and sculpted what followed. Then the paradox sharpens at the moons. Radiation sterilizes surfaces, bleaching ice and manufacturing oxidants, but tides heat Europa and Ganymede, flexing their interiors and sustaining oceans that may be habitable. A world can be deadly at the surface, yet chemically promising below. What does safe even mean in a place like this? So what makes Jupiter terrifying? Extreme magnetism, lethal radiation, relentless storms, and gravity that reshapes impact risk under the sun. The Great Red Spot is only the emblem, because the whole atmosphere is a heat engine that never truly rests. From Earth, it returns to a quiet dot, now read as a warning light. Beauty is distance, and power leaves fingerprints everywhere, even when the sky looks calm. From Earth, Jupiter passes for a calm jewel, but every chapter pulled that illusion apart with scale, physics, and consequence. We followed the planet from its surfaceless storm engine, down through crushing layers toward metallic hydrogen, then back outward into a magnetosphere that turns empty space into machinery. There, rotation and moon-fed plasma build a magnetic empire, one that traps particles, breeds auroras, and hardens radiation into a kill zone that can erase a spacecraft's memory. We watched the Great Red Spot as both monument and warning, a centuries-old vortex now shrinking and changing, while its reds and browns still keep their chemical recipe partly hidden. We traced how Jupiter's internal heat keeps the atmosphere restless, and how its interior structure, perhaps blurred by an ancient collision, still shapes the field that shapes the belts. Then we widened the frame to gravity, the quietest weapon of all, carving resonances into the asteroid belt, capturing and flinging comets, and rewriting impact odds on worlds that never asked to be part of the experiment. Even our return missions, flying on borrowed time behind titanium vaults and careful trajectories, proved the final point, that understanding Jupiter means entering a place where the environment actively fights back. Taken together, Jupiter is not one threat but a linked system. Storms, interior, magnetism, radiation, and gravity. Each feeding the next, each extending its reach far beyond the clouds. And that is what makes Jupiter genuinely terrifying. Not simply that it can kill machines or crush probes, but that it has been shaping, threatening, and protecting the solar system since before Earth had an ocean. The same giant that can sling comets toward us can also eject them into darkness. And the same physics that sterilizes a moon's surface can help power an ocean beneath it. So the question was never guardian or villain, But architect of what kind of life, under what kind of risk? Jupiter looks peaceful because distance turns violence into a point of light, and because our eyes mistake steadiness for safety. But the planet is a reminder that the universe does not need malice to be dangerous. If beauty can hide a furnace, then the night sky is not a backdrop. It is a map of forces, quietly deciding what survives long enough to matter. If you want to keep following what Jupiter still keeps hidden, stay with the data, the missions, and the unanswered mechanisms, because the closer we measure, the more honest the wonder becomes. And that is what makes Jupiter genuinely terrifying. Not simply that it can kill machines or crush probes, but that it has been shaping, threatening, and protecting the solar system since before Earth had an ocean. The same giant that can sling comets toward us can also eject them into darkness, and the same physics that sterilizes a moon's surface can help power an ocean beneath it. So the question was never guardian or villain, but architect of what kind of life, under what kind of risk. Jupiter looks peaceful because distance turns violence into a point of light, and because our eyes mistake steadiness for safety. But the planet is a reminder that the universe does not need malice to be dangerous. If beauty can hide a furnace, then the night sky is not a backdrop. It is a map of forces, quietly deciding what survives long enough to matter. If you want to keep following what Jupiter still keeps hidden, stay with the data, the missions, and the unanswered mechanisms, because the closer we measure, the more honest the wonder becomes.